As NASA's robotic lander, InSight, completes its journey to the Martian surface, the successful touchdown is met with celebration. Far above, another mission, the European Space Agency's ExoMars satellite, simultaneously begins its own scientific investigation of the Ochre planet. The majestic stereo images returned from orbit present a world of dynamic textures and forms, a planet that is slowly beginning to share its deepest secrets. The lead scientist for the InSight mission explains that while numerous past expeditions, including rovers and orbiters, have returned truly exceptional science, their measurements have been limited. These valuable observations have essentially only scratched the surface of Mars. Our understanding of the planet's surface, its thin atmosphere, and even its ionosphere is quite extensive. However, what happens a mile beneath the surface, let alone 2,000 miles down toward the planet's center, remains largely a mystery. InSight is the very first mission designed specifically to investigate the vast, unexplored interior of Mars. The fundamental concept behind the mission is to generate the first ever map of Mars's deep structure. The science team intends to chart the thickness of the crust, determine the size of the core, and analyze the composition of both the mantle and the core. The goal is to produce the first comprehensive blueprint of the planet's deep interior. This is the mission that will finally conduct the science and gather the measurements that the principal investigator notes he has been personally and professionally anticipating for over 3 decades. He recalls that as a graduate student, his research required knowing the thickness of the Martian crust, a piece of data that simply did not exist. It was clear that seismology was the method needed to acquire it, and he hoped that one day someone would place a seismometer on Mars to get that measurement so he could advance his work. He reflects on what a remarkable journey it has been to find himself in the position of leading the very mission that will place that instrument on the planet. With that information, he can now return to the work he was trying to complete 30 years ago, an experience he describes as an amazing feeling. The InSight mission is poised to deliver seismic information about Mars that scientists have sought since the very first lander, Viking. That early mission carried a seismometer, but for a number of reasons, it never returned any usable seismic data. In the years since, there have been many other attempts to place seismometers on the Martian surface for compelling scientific reasons, but one by one, they were unsuccessful. Now, science is on the verge of finally having a working seismometer on Mars that will transmit the long-awaited data. That seismic information is incredibly important because it allows scientists to understand the size of the crust, mantle, and core, as well as the properties of each layer, which are the fundamental internal components of any rocky planet. From an engineering perspective, one of the most interesting challenges of the InSight mission is likened to playing a claw game at an immense distance. The team will use a grapple on the lander's robotic arm to pick up an instrument, lift it from the deck, and carefully place it on the Martian ground. The engineer compares it to operating a claw machine on Mars, but without the benefit of a joystick. Following this delicate maneuver, a wind and thermal shield will be lowered over the seismic instrument, protecting it from the harsh environment. The second instrument, a heat flow probe, will then be placed on the ground, where over time it will hammer itself down to take readings from below the surface. InSight is a mission built on extensive international partnerships. It truly takes a global effort to produce such an exciting endeavor. Most of the primary science instruments are supported by international collaborators. The seismometer instrument, for example, receives support from French, German, Swiss, and UK partners. The heat flow and physical properties probe is provided by Germany, with additional support from Poland. While InSight is a mission to Mars, its implications reach much further. In a sense, it functions as a time machine. It is measuring the planetary structure that was locked into place 4.5 billion years ago. This allows scientists to travel back in time to understand the processes that formed Mars shortly after it accreted from the solar nebula. By studying Mars, we can learn more about Earth, Venus, Mercury, the Moon, and even exoplanets orbiting other stars. Elsewhere in the Martian system, ESA's Trace Gas Orbiter mission arrived some time ago. Since then, the 3.5-ton spacecraft has been using the planet's upper atmosphere to gently brake, a long process designed to gradually adjust its orbit. Inside ESA's Planetary Missions Control Room in Darmstadt, Germany, flight controllers have been running system checks and commissioning the instruments on the ExoMars Trace Gas Orbiter. Now, it is ready to commence its science phase. Mission personnel note that it has been a long journey since their arrival at Mars in October 2016. The spacecraft underwent a year-long aerobraking period, which was necessary to reduce its orbital period from several days down to just 2 hours, the optimal timing for science observations. There is enormous anticipation for the coming months, as the orbiter will finally be able to demonstrate the full capability of its instruments, showing their accuracy and the quality of data they can produce, from pictures to spectra. It will also be a period of joint observations with ESA's previous Mars spacecraft, Mars Express, which remains operational after 15 years. For the European Space Agency, having 2 spacecraft around Mars in scientifically complementary orbits is an exciting prospect that will certainly enable some very interesting discoveries. The ExoMars mission will also serve a dual purpose when its partner rover is sent to Mars in the near future to search for signs of life. In addition to being a science orbiter, it is also a communications satellite. This relay function allows it to communicate with all landers and rovers on the surface of Mars, which currently include NASA's Curiosity and Opportunity. Some tests of this capability were performed shortly after its arrival, and a new campaign is beginning to calibrate and determine the best performance for relaying data. The primary mission of the Trace Gas Orbiter, however, is to identify the gases present in the Martian atmosphere, with a particular focus on methane, which has been hinted at in previous observations. The detection of methane in the Martian atmosphere, first by Mars Express and later by NASA's Curiosity rover, sniffing the air with specialized sensors, presents a compelling scientific puzzle. What stands out is the very short lifespan of methane, which is broken down by the ultraviolet component of sunlight in just a few hundred years. Its persistent presence means something must be actively replenishing it, leading to a fundamental question about its origin. The gas cannot form in the atmosphere itself. It has to be emanating from the surface or the subsurface. Uncovering the processes that produce it is a primary goal. One explanation could be geological reactions involving minerals and water deep underground. An alternative, and more profound, possibility involves microbial life buried far beneath the surface. These organisms could be producing the gas today, or perhaps they did so long ago, leaving behind trapped reservoirs of methane that are now slowly being released into the air. To determine whether the source of this methane is geological or biological, scientists are using the powerful spectrometers on orbiting spacecraft. On our own world, a remarkable 95% of methane originates from living organisms, a fact that adds weight to the search on Mars. The ExoMars rover, planned for a 2021 landing, is designed to further this investigation by drilling up to 2 meters beneath the surface, hunting for direct evidence of life. This rover, along with NASA's rovers and landers, will rely on the orbiter as a crucial communications link to Earth, highlighting how Mars exploration is a collaborative, international endeavor, where every mission contributes to our collective understanding of this alien world, a place that some humans might one day call home. Planetary exploration is inherently exciting, but Mars holds a unique fascination. It is a world that we can imagine ourselves walking on, and there is a sense that in the not-too-distant future, people will indeed walk on its surface. This vision, combined with the tantalizing idea that some form of life might have once existed, or could even persist today underground, makes Mars an object of special significance. Curiosity landed in Gale Crater, a location known to be an ancient lakebed. A few months after its arrival, the rover drilled into sedimentary rocks and, using an instrument called SAM, detected the presence of organic molecules. The SAM instrument identified a variety of these molecules within sediment from the crater's former lakebed. The importance of this finding is that it provides a much higher degree of certainty that organic molecules are indeed preserved near the Martian surface, something that was not known before. What remains a mystery, however, is the source of these organic compounds. The data is not yet sufficient to determine their origin, but with further drilling and exploration, it may become possible to learn whether they came from life, from geological processes, or were delivered by meteorites that fell into the ancient lake. For now, the question remains open, but the hope is that an answer will eventually be found. The Curiosity rover is searching for carbon-based organics, and the SAM instrument made its new detections through a process of intense heating. It warmed samples of crushed rock to very high temperatures, exceeding 1,000 degrees Fahrenheit. This procedure vaporized the samples, which in turn released several types of small hydrocarbons, such as benzene and propane. The fact that these hydrocarbons were released at such extreme temperatures is a critical clue. It suggests they may be fragments of much larger, heavier molecules locked within the rock, similar in nature to kerogens found on Earth. Kerogens, which are found in rocks like black shale and coal, are the preserved remnants of ancient plants and bacteria. Other organic compounds have also been detected, including thiophene, which contains sulfur introduced through geological processes. This sulfur appears to act as a natural preservative, binding organic molecules together and making them more resistant to oxidation. This protective mechanism allows them to survive for millennia. These organic molecules could represent food for life, or they could be the product of life itself. Alternatively, they might originate from something entirely different, like geology or meteorites that were deposited into the lake long ago. While their source is not yet known, there is a story locked within them, and scientists are working to uncover it. Although researchers still do not know if the organics discovered on Mars have a biological origin, the discovery of such ancient material preserved right at the surface is an exciting development. This finding is also a powerful encouragement for future exploration. For a time, Curiosity continued its mission, traveling across the landscape, finding interesting rock outcrops, drilling holes, and taking samples. Then, without warning, something went wrong. The drill's feed mechanism, which is responsible for extending and retracting Curiosity's drill bit, failed to move when commanded. In its original design, the drilling process began with two stabilizer posts touching the rock to steady the robotic arm. The feed mechanism would then push the bit forward into the rock. Without a functioning feed mechanism, that method was no longer possible. To solve this dilemma, engineers turned to the testbed, using Curiosity's Earth-based twin to work out a new approach. The team of engineers and scientists spent months devising a way to collect and deliver rock samples without relying on the feed mechanism. The solution they developed is a new technique called feed-extended drilling. In this method, the stabilizers are not used. Instead, the drill bit is locked in a forward position, extended past the stabilizers. Moving the drill directly into a rock and pulling it back out safely without the stabilizers is a significant challenge. The entire robotic arm, rather than the feed mechanism, is now used to place the bit onto the rock and press it forward during drilling. After making contact, the arm applies a light preload to create a shallow pilot hole. A force sensor in the robotic arm provides Curiosity with a sense of touch, which allows it to adjust its own motion and avoid getting the bit stuck, much like a person might adjust their arm while drilling into a wall at home. After the hole is drilled, a similar, carefully controlled technique is used to retract the bit without it getting jammed. With the design and construction of the rover 2020 well underway, engineers were able to ensure that such a problem would be avoided with Curiosity's cousin, which was scheduled to land in Jezero Crater in 2020. That year was set to be a banner year for the exploration of Mars. In addition to the launch of NASA's Mars 2020 rover, the European Space Agency and Roscosmos were sending their ExoMars rover to the Red Planet. The Mars 2020 rover and its companion helicopter will undoubtedly expand the search for life, whether past or present. However, the most significant advance in organic analysis is expected to be a true game changer. Both rovers will carry an instrument called MOMA, the Mars Organic Molecule Analyzer. The Mars Organic Molecule Analyzer, known as MOMA, represents the largest and most complex instrument on the rover. Its critical components, including its mass spectrometer subsystem and main electronics, were constructed and tested at NASA's Goddard Space Flight Center, a facility that also provided mass spectrometers for NASA's Curiosity rover and the MAVEN orbiter. MOMA's design is a careful marriage of proven hardware and innovative new technologies. The instrument's operation can be understood through its two primary modes. In its gas chromatograph mode, a pulverized sample of Martian rock is introduced into an oven and heated to 900 degrees Celsius in just 2 minutes, a process that vaporizes the material. These hot gas molecules then flow into a narrow tube that stretches 20 meters long. Inside the tube, special coatings cause molecules with different chemical structures to slow down at different rates, which effectively separates the complex mixture over time. Afterward, a beam of electrons gives the molecules a positive electric charge, ionizing them and deflecting them toward a linear ion trap. Within the trap, the ions are contained by a fluctuating electric field and are then sent to a detector to ascertain the sample's chemical makeup. While gas chromatography has been employed to study Mars since the Viking program, MoMA possesses a second method for preparing samples that is entirely new to planetary exploration. In what is called laser desorption mode, a sample is situated beneath a powerful ultraviolet laser. An energetic pulse of light builds inside the laser and is then fired in a billionth of a second, concentrating all of its energy onto a spot smaller than a grain of sand. This action instantly vaporizes a portion of the sample, which is key to releasing large organic molecules that might be destroyed by the oven's high heat. The laser shot also ionizes some of the molecules in the process, which allows the resulting vapor to travel directly to the linear ion trap. Any neutral molecules are removed by a vacuum, while the charged ions that remain are sent to the detector to have their chemical composition analyzed. This laser desorption technique will enable MoMA to detect long molecules such as lipids, the fundamental building blocks of cell membranes, marking a significant leap forward in the ongoing search for life on Mars. The question of life on the red planet is among the most vital in planetary science, and the evidence could be buried just below the surface. With the assistance of MoMA, we are taking one more step toward uncovering the answer, and the images it helps produce will pave the way to a new understanding of life in our solar system. While large, sophisticated instruments define one approach to exploration, another is unfolding on a much smaller scale with CubeSats. For some time, these have been primarily in the domain of universities and other institutions, used to teach and gain experience in space. They are valued for being low-cost, lightweight, and highly adaptable. Furthermore, they are relatively easy to send into orbit. Now, the business world is looking at these microsatellites with significant plans for the future. A traditional satellite is an industrial and technological marvel, designed and built from the ground up for a specific purpose and a long life expectancy. Although some communications and global positioning satellites are constructed on off-the-shelf platforms to help reduce costs, launching them is no simple task. Weighing as much as 50 tons, they must be placed in a geosynchronous or high polar orbit, which requires expensive launch facilities. The CubeSat, or microsatellite, originally devised as a training tool for university students, has since taken on a life of its own. It serves as a low-cost alternative to conventional satellites in particular roles, and for new purposes not previously imagined. A CubeSat is a nanosatellite built to a standard box-like dimension, with the base unit being 10 by 10 by 10 centimeters. Multiple units can be combined, creating, for instance, a 3-unit CubeSat measuring 10 by 10 by 30 centimeters, with all the satellite's equipment needing to fit inside that volume. The origin of CubeSats traces back more than a decade in the U.S., where university professors were searching for ways to let their students build and fly satellite hardware during their degree courses. This was envisioned as a very low-cost path for universities to educate their students in practical engineering skills. Recently, university student teams across Europe have been making their final preparations for ESEO, the European Student Earth Orbiter, a project intended to prepare the space workforce of tomorrow. These student teams designed, constructed, and tested the essential parts for the mission through its entire project lifecycle. ESEO involved several hundred students, and it was considered to have achieved its main educational objectives even before its launch. Placed into a polar orbit by a SpaceX Falcon 9 dedicated to small satellites, ESEO was released to begin its mission. Aboard the satellite is a radio amateur communication system developed by a university in Wrocław and AMSAT UK, which enables ESEO to transmit real-time data to schools and universities for science and engineering purposes. One student who participated in the LMP project described it as a personal journey, having designed a component for it and based their thesis on that work. Another involved in developing the satellite's power distribution unit shared the amazing feeling of knowing their device would soon be in space, working as intended. The project was recognized as a complex and challenging activity for all the student teams. It provided an opportunity to teach students specialized skills not commonly found in academia. For one observatory, the SEO project supplied the competence needed to build future scientific instruments, fostering both technical ability and connections with the European Space Agency. The lessons learned were invaluable for developing their own subsequent missions. Some prior evidence has suggested that lightning produces gamma rays, and a new mission is the first satellite dedicated to investigating if, how, and where these emissions occur. While others have seen signs of this, there has never been a satellite tasked with looking down at Earth specifically for these terrestrial gamma ray bursts. The team plans to create artificial signals similar to lightning to verify that the onboard systems are filtering the signals correctly with the logic programmed into HDL code. A core tenet of the CubeSat program is to involve undergraduate students at all levels, from design and construction to theory and data acquisition. In every way, these projects are training the next generation of space scientists and satellite engineers. The moment the launch is successful and students know their work is part of that satellite, with data coming in, is an experience that will remain with them throughout their lives. The mission of the InSight lander to Mars presented an ideal setting to determine if CubeSats could be applied to a major interplanetary endeavor. The journey began with the liftoff of a United Launch Alliance Atlas V rocket, its RD-180 main engine igniting to generate more than 860,000 pounds of thrust. Flying alongside the InSight spacecraft were two small but significant companions known as Mars Cube 1, or MARCO. These twin spacecraft, designated MARCO A and MARCO B, were conceived as a technology demonstration, representing the very first use of the miniature, modular, CubeSat spacecraft design in the vastness of deep space. Each of these briefcase-sized craft was launched on the same rocket as InSight, but traveled independently of the main lander on its own trajectory to the Red Planet. Their primary function was to carry out a number of communication and navigation flight experiments during their long voyage. In the lead-up to InSight's landing, NASA was careful to emphasize the experimental nature of the CubeSats, framing them as a high-risk, high-reward test. And yet, the MARCO spacecraft performed their intended function perfectly. As InSight undertook its perilous entry, descent, and landing sequence, the two tiny probes successfully received the UHF telemetry signals from the lander. They then immediately rebroadcast this critical data stream at X-band frequencies, which was in turn received by NASA's Deep Space Network on Earth. This remarkable achievement served as a powerful vindication, firmly establishing CubeSats as another valuable and viable tool in the ongoing exploration of deep space. To top it all off, as it flew past the planet, MARCO B managed to capture a striking photograph of Mars and successfully transmit it all the way back home. This success has since ignited a rush to exploit the full potential of CubeSats. All around the world, scientists and engineers have begun designing, building, and launching a diverse array of these small spacecraft, with each design tailored for highly specific scientific missions, or for testing novel technologies in the unique environment of space. The launch industry has been quick to respond to this burgeoning demand, developing and flying dedicated launches specifically for the emerging small satellite market. Among the companies serving this new sector are established players like SpaceX and Europe's Arianespace with its Vega launcher. A particularly prominent example is Rocket Lab, whose Electron vehicle has already begun flying commercial CubeSat launches and is now planning to offer a regular monthly service. A representative from the European Space Agency, or ESA, explained that his own connection to the field began a decade earlier, during his time working in the agency's education office. In that capacity, he was responsible for managing university CubeSat projects. These student-led initiatives, he recounted, were eventually chosen to fly on the maiden flight of the Vega launch vehicle. In fact, a total of 7 CubeSats built by universities were carried into orbit on that inaugural Vega mission. He noted that many of the students who were deeply involved in those formative projects went on to graduate and subsequently form their own spin-off companies. In a fascinating turn of events, these very companies, which were born from academic exercises, now form the essential basis of today's vibrant and growing CubeSat industry. Looking toward the future, he observed that the same fundamental technologies being exploited for terrestrial aerial drones are also being incorporated into CubeSats. He offered the compelling thought that this parallel technological evolution will ultimately enable CubeSats to become the autonomous drones of the space domain. With such advanced capabilities, he believes these small spacecraft will gain the performance necessary to execute highly complex tasks. He painted a picture of them carrying out autonomous navigation, performing delicate close proximity operations around other target objects, and even flying together in precisely coordinated swarm formations. These advanced architectures, he continued, might one day see CubeSats performing autonomous rendezvous and docking maneuvers, effectively acting as intelligent building blocks to assemble much larger structures in space. He emphasized that when ESA undertakes its CubeSat projects, it combines a standard engineering approach with privileged access to the agency's world-class facilities and deep technical know-how. This synergy, he explained, provides significant added value to ESA's member states, ensuring that the probability of mission success is maximized even within the characteristically tight financial constraints of each project. He pointed to a strong record of success, highlighting that ESA had already flown one technology, CubeSat in orbit, GOM-X-3. That mission was very successful and was completed when the satellite recently re-entered the atmosphere. Currently, the agency is preparing to fly another CubeSat called Kármán, which he described as a very exciting and challenging project designed to demonstrate re-entry technologies. Beyond that single mission, another 4 technology CubeSats are already in development, and conversations are underway with member states about initiating many new projects for technology demonstrations in the years to come. The use of microsatellites for commercial and industrial purposes is a rapidly growing field of interest, as is the parallel concept of the Internet of Things. One company, Fleet, has combined these two powerful domains into what may become the next great technological revolution. It is a name that could soon be added to a list that includes household giants like Microsoft, Google, and SpaceX. A representative from the company explained that the concept of the Internet of Things, or IoT, probably began to materialize about 5 to 10 years ago. It arrived with bold forecasts of 25 billion devices coming online, signaling a fourth industrial revolution that would connect everything and fundamentally alter our lives. He finds it helpful to separate this broad concept into 2 distinct categories. The first is the consumer-facing world of smart cities, where our daily lives will be transformed by interconnected devices, from a fitness band that communicates with a refrigerator to self-driving vehicles and intelligent traffic management systems. The second, more industrial category is what he calls smart industry. This applies to what happens in remote areas, such as on a massive farm, at a sprawling oil and gas facility, or within a large-scale mining operation. This is the arena for a heavy industrial revolution. At its heart, the Internet of Things is the idea that we are changing the very way we operate. Having spent the last 40 years connecting people and integrating computers into factories to the point where a day without one seems impossible, we are now poised for a similar shift. Over the next 40 years, he believes, connected things will change industry in the same profound way that computers did. He offered the example of a large farm where suddenly everything becomes connected. This vast network might include thousands of individual sensors, monitoring everything from the nutrient content in the soil to the precise location of livestock and real-time weather station data. This constant flow of information will allow the farmer to understand their operations with an unprecedented level of detail, empowering them to solve some of the planet's most significant problems, such as water leakages and the impacts of drought. This same principle, he noted, extends to transport and logistics, where tracking individual pallets and containers of fruit as they travel across the globe could help to address the staggering estimate that 60% of our food is wasted somewhere in the supply chain. These are the kinds of big changes that can happen, all driven by connecting small sensors. The fundamental problem, he articulated, is that these major industries largely operate where there is no 3G, 4G, or even 5G coverage. While terrestrial infrastructure is built to cover populations, it leaves 95% of the world unconnected. This vast, unserved territory is exactly where our farms, our mining and gas companies, and our shipping containers are. This is a problem that terrestrial infrastructure cannot solve. The solution, he stated, must therefore come from space. The potential for constellations or swarms of CubeSats to become powerful research and communication tools is now starting to be explored in earnest. The ability to track almost anything, anywhere across the surface of the planet is now a reality. As this new era of connectivity unfolds, the possibilities seem almost endless. From the vantage of low Earth orbit, a satellite constellation can provide coverage for nearly every part of the globe. For certain applications, a single pass per day is more than sufficient. While this frequency is not suitable for high bandwidth needs like streaming on YouTube or making calls on Skype, it is perfectly adequate for the Internet of Things. Monitoring a valve, checking a soil moisture sensor, or tracking the location of livestock does not require constant minute-by-minute updates. A daily check-in from orbit is ideal for these purposes. However, an intriguing shift occurs as the constellation grows. Once a fleet reaches a certain density, perhaps around 100 satellites or even fewer, the latency drops dramatically. This opens the door to high-pressure, emergency applications in fields like safety and security, where data must be sent and received almost instantaneously. A key advantage of this model is its scalability. A company can begin operations and serve a global client base after launching just a single satellite. This was the journey for the startup fleet, which sent its first 4 satellites into space in a remarkable 24-day period. Their initial launch partner was Rocket Lab for what was the company's first commercial nano-satellite mission, creating a palpable sense of anticipation about the outcome. Subsequent launches involve partners like SpaceX and India's PSLV. The acceleration of their manufacturing process is just as noteworthy. Building their first satellite took almost a full year, and the second required 2 months. By the time of the Rocket Lab launch, the entire timeline from the start of construction to booking a flight and reaching orbit had been compressed to an incredible 4 weeks, highlighting a broader revolution in the launch sector that enables rapid deployment into space. This startup's approach appears to be perfectly timed. By connecting inexpensive terrestrial sensors for almost any purpose to a network of CubeSats, they can upload data and deliver it to clients over the internet. The customer base for these sensors is already significant, ranging from the world's largest oil and gas corporations to vast agricultural farms in South America. We are entering an era where small startups can achieve a massive customer impact that has eluded some billion-dollar legacy satellite companies for years. It signals a time to look at satellites not as a niche industry, but as the foundation for what will very quickly become billion-dollar enterprises. The potential for this system to drive efficiency and reduce waste on a global scale is immense. Our planet requires better monitoring and more efficient use of its resources, from conserving water and preventing food waste to ensuring human safety. A network of millions of sensors promises to change the world permanently, and that number could eventually grow into the billions. Fleet began with a vision they called 1F, a plan to connect 1 million devices across the planet. Their roadmap extends to a second constellation, 2F, and ultimately to 3F, which sets its sights on Mars. The possibilities for space exploration are truly exciting. Imagine quick and efficient data networks deployed on the Moon, Mars, and beyond, or even swarms of CubeSats surrounding an asteroid or a spacecraft during a rendezvous, sending back a constant stream of data and video. The scope is limitless. One could envision a constellation dedicated to tracking every robot and asset on another world, ensuring their locations are always known. When future entrepreneurs establish operations on Mars, they will bring a vast amount of equipment, and tracking it all will be a complex but essential task. CubeSats offer a way to establish such a network quickly. While moving a large, traditional satellite to Mars is a long and arduous process, a swarm of smaller satellites can be launched with the expectation that a sufficient number will arrive to form a functional network. As humanity begins to explore and settle other worlds, this same need for monitoring and responsible stewardship will arise, a responsibility that companies like Fleet may one day help to shoulder. Closer to home, orbiting between us and our star, are 2 worlds often hidden within the sun's glare. Venus, the first and brightest point of light in the evening sky, and Mercury, a fleeting shadow that occasionally transits the solar disk, are visible primarily at sunrise or sunset. They represent half of our solar system's terrestrial planets, yet we know remarkably little about them. As we begin to take a closer look at these companions, they are posing more questions than they answer. Mercury, the innermost planet, orbits closest to our Sunday. There, days are longer than years, and its path is a pronounced ellipse, carrying it from 47 million kilometers to 70 million kilometers from the Sunday. Its proximity to our star's intense light makes it exceptionally difficult to observe from Earth, leaving it as an enigma in the story of our solar system's evolution. Scientists point out that Mercury is a planetary anomaly. Among the terrestrial planets, there is a predictable relationship between size and density, but Mercury does not follow this rule. It is far more dense than a planet of its size should be, which suggests something went wrong or was highly unusual during its formation. Only 2 probes have ever been sent to investigate Mercury, and just one has successfully achieved orbit. Reaching the planet is a profound challenge due to its high orbital speed and the immense gravitational influence of the Sunday. Mercury is a planet of extremes. Daytime surface temperatures can reach 400 to 450 degrees Celsius, akin to being inside a pizza oven, while nighttime temperatures plummet to around minus 175 degrees Celsius. It completes an orbit of the Sun every 88 days, and at its closest approach to Earth, it is still 77 million kilometers away. The first detailed imagery of Mercury was captured by the U.S. probe Mariner 10 Sol 1974. The spacecraft lacked sufficient fuel to slow down and enter orbit, so it instead orbited the Sun, allowing it to pass by Mercury 3 times. These flybys yielded 2 intriguing and seemingly contradictory observations. First, they revealed that Mercury has a magnetic field similar to Earth's, which is highly unusual for a planet with such a slow rotation. Second, images showed a surface that was heavily cratered, with very little evidence of volcanic activity or crustal movement. The most recent mission was Messenger, launched in 2004. To shed enough velocity to enter orbit, it performed several planetary flybys of Earth, Venus, and Mercury itself. The journey took 6.5 years before it could finally settle into orbit around Mercury in 2011. The mission highlighted the extreme thermal environment. A spacecraft near Mercury is subjected to intense heat, not only from the Sun, but also from the planet itself, which reflects solar radiation like a thermal mirror. This dual heating from the side and below can easily destroy a conventional spacecraft. To become operational, the Messenger spacecraft had to enter a very loose orbit around Mercury. This approach was a careful necessity, as the thermal conditions near the planet are so extreme that a closer, more conventional orbit would have been unsustainable. The probe's primary mission was a remarkable success, completed within just 1 year, during which it mapped the entire globe using a mosaic of about 100,000 images. With a significant amount of fuel still in reserve, the mission's lifespan was extended far beyond its original plan. For the next 10 years, Messenger continued to transmit a wealth of information and observations back to Earth. Its data provided new insights into Mercury's magnetic field, the structure of its magnetosphere, and the complex effects of solar wind plasma. The mission also conducted detailed studies of Mercury's tenuous atmosphere. This atmosphere is so low in density that it is constantly being stripped away from the planet, forming what is known as an exosphere. This process creates a faint tail of particles trailing away from the Sun, within which scientists could identify elements like sodium, calcium, and magnesium. Further analysis, using spectrographic imaging of the surface materials, has only deepened the mystery surrounding the planet's unusually high metallic density. What stands out is that the observations from Messenger do not align with the prevailing theories of planetary evolution, suggesting that our fundamental models may need to be completely overhauled. Another intriguing detail emerged from the planet's polar regions. There, in the permanently shadowed interiors of deep craters, Messenger detected the distinct presence of water ice, a discovery that mirrors similar findings on our own moon. In 2014, the probe was directed to fly much closer to the surface, descending to an altitude as low as 50 kilometers. From this new vantage point, it captured images at a much greater resolution, searching for more detailed evidence of the planet's geological history. Left to its own devices, the probe's orbit would have continued to decay, leading to an eventual impact on the surface. However, there was just enough fuel remaining for 3 final trajectory alterations, which were used to briefly increase its altitude. These maneuvers granted the probe a short but valuable time extension, allowing it to continue its scientific work into 2015. A third mission to Mercury is now underway, a collaborative effort between the European Space Agency and the Japanese Space Agency, JAXA. The mission is named Bepi Colombo in honor of the Italian mathematician Giuseppe Colombo, who was the first to develop the gravity assist maneuver for NASA's Mariner 10 probe. Bepi Colombo actually consists of two separate orbiters, the ESA Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter. Scientists leading the mission have stated that their primary goal is to understand the fundamental nature of the planet itself. They want to determine what materials make up its surface, measure its temperatures, and observe its interaction with the solar wind. A particular point of focus is Mercury's magnetic field, which, like Earth's, is a dynamo field whose origins they hope to better understand. The Japanese orbiter, the MMO, will concentrate on the magnetic field and the environment around the planet, while the ESA probe will focus its instruments on the planetary surface. Much like the two missions that preceded it, Bepi Colombo will use gravitational assists from Earth and Venus to gradually slow its speed and settle into orbit around Mercury. This intricate trajectory is expected to take approximately 7 years to complete, relying on solar electric motors for sustained deceleration, with a final burn from a conventional rocket engine for orbital insertion. Once they arrive, the probes are expected to last for 1 to 2 years in Mercury's harsh environment. The two craft are outfitted with a suite of the most advanced scientific instruments available, including a laser altimeter, a magnetometer, infrared and ultraviolet spectrometers, and cameras capable of imaging in X-ray and high-resolution stereo. Bepi Colombo is specifically designed to seek answers to a list of enduring questions about this enigmatic world. Why is the planet so dense? How did it form? Is Mercury still tectonically active? Why is there no identifiable iron on its surface? In the absence of a significant ionosphere, how does its magnetic field interact with the solar wind? And how is that magnetic field generated in the first place? Researchers explain that our existing theory for how planetary systems form was based on explaining our own solar system, and for a long time, it worked well. However, with the discovery of numerous extrasolar planets around other stars, it has become clear that many of them do not fit our models at all, indicating that something fundamental is missing from our understanding. They believe that studying the special cases, the worlds like Mercury that are difficult to explain in detail, can be tremendously helpful. By finding answers to some of these questions, Bepi Colombo will help us better understand how our entire solar system was formed 5 billion years ago. It is often the first and brightest point of light we see in the night sky. In some ways, Venus is our sister planet, our closest planetary neighbor in both distance and diameter. Despite its proximity, however, Venus is incredibly difficult to reach, and it is a profoundly strange world once you arrive. In the early days of the solar system, it is thought that Venus and Earth must have been very similar. But then, at some point, something happened that sent Venus on a drastically different evolutionary path. One of the most bizarre facts about Venus is that it is the only planet in the solar system that takes more time to rotate once on its own axis than it does to orbit the Sunday. A leading theory proposes that a major cataclysm occurred in the planet's early history, where it collided with another large object, an impact so violent that it essentially stopped its original rotation. The consequences of this event were catastrophic. Without the protective effects of a faster rotation, the planet lost its water and became completely dry. This, in turn, led to a runaway greenhouse effect that caused the surface temperature to climb to the scorching levels we see today. One of the main differences between Venus and Earth is that Venus lacks a global magnetic field, which means the way it interacts with the Sun is completely different. To understand how Venus became the world it is, and why it has no oceans, it is crucial to first understand this unique relationship between the star and the planet. Both the Soviet Union and the United States sent probes to Venus with some success. 3 of NASA's Mariner spacecraft performed brief flybys, while the Soviet Venera probes successfully entered the atmosphere and touched down. Some of these landers survived for only a few minutes, but in that time, they managed to send back tantalizing images of an almost serene vista. NASA later sent 2 more probes, Pioneer Venus 1 and 2, with the latter deploying 5 small probes onto the surface. The Soviets continued their ambitious Venera program with 4 more successful landers and orbiters. Later, 2 Russian Vega missions deposited atmospheric probes as they flew past Venus on their way to Halley's Comet. The atmosphere of Venus is a source of incredible fascination because it is so profoundly different from Earth's. Scientists believe that understanding what causes these differences could provide vital insights into climate change on our own planet. Venus has a very dense atmosphere, composed of 97% carbon dioxide, which creates an extremely powerful greenhouse effect. The temperature down on the surface is more than 450 degrees Celsius, and the surface pressure is 92 bars, which is almost 100 times greater than on Earth, making it a very unpleasant place to be. A great atmospheric mystery is found high up in the clouds, about 100 kilometers from the surface. Here, the wind speeds are incredibly high, traveling at 300 kilometers an hour and circling the entire planet every 4 to 5 days. What scientists do not yet understand is why at the surface the winds are very gentle, while high above they are so extraordinarily fast. The atmosphere of Venus is profoundly different from that of Earth, a realm of high-speed dynamics. A pivotal chapter in understanding this world began in 1989 when the Space Shuttle Atlantis carried the NASA probe Magellan into orbit. Deployed from the payload bay, Magellan set off for Venus on a 5-year mission to create a comprehensive radar map of the planet's surface. By peering through the dense, perpetual cloud cover, its radar slowly unveiled the true face of our planetary neighbor. What emerged was a geologically young surface, marked by a scarcity of impact craters. The landscape was dominated by widespread volcanic activity, with vast lava flows and expansive lava plains. Intriguingly, there was very little evidence of wind erosion, and unlike the tectonic plates of Earth, the surface was characterized by global rift zones. For a long time, Magellan was the last Venus probe sent by NASA. 12 more years would pass before the planet came under close scrutiny again, this time by the European Space Agency's Venus Express. To ensure a long mission life by conserving fuel, the probe utilized the technique of aerobraking, using the friction of the upper Venusian atmosphere to carefully settle into orbit. Among the mission's very interesting discoveries was an enormous vortex, a huge cloud formation at one of the poles. In some ways, it looked similar to a hurricane on Earth, but scientists noted this was a permanent, long-standing event. They reported that they do not understand how it formed, why it is there, or how it might evolve. An additional puzzle emerged from atmospheric measurements. When Venus Express arrived 8 years ago, it detected winds moving at a rapid 300 kilometers per hour. But over the course of its mission, those winds had actually accelerated, with the probe later observing speeds of 400 kilometers per hour. Researchers acknowledged they could not really explain why this had happened. More questions were raised by the planet's absent magnetic field. Without this protective shield, Venus is essentially a large rocky body, its atmosphere and ionosphere sitting directly in the path of the supersonic solar wind. This stream of particles, carrying the interplanetary magnetic field, slams into Venus but cannot penetrate the ionosphere. As a result, the field lines are described as piling up ahead of the planet. This constant bombardment by the solar wind is thought to be stripping away the atmosphere, forming a long, comet-like tail that stretches far out into space. The Pioneer Venus orbiter was the first spacecraft to thoroughly explore that nightside region where the atmosphere is escaping. It discovered a mysterious phenomenon that has yet to be explained: ionospheric holes. Scientists described the effect as if one were flying from pole to pole through the plasma on the night side, only to have the ionosphere suddenly disappear, then reappear. These features are like chasms in the sky, large holes where the ionosphere is simply absent. The Pioneer Venus orbiter's measurements inside these structures revealed very little plasma, but a strong magnetic field. From this, it was suggested that they were essentially magnetic structures sitting on the night side. Wishing to investigate further, researchers later used Venus Express to look for these phenomena. They observed an exciting, strong magnetic field line as expected, accompanied by very quiet plasma signatures. This confirmed that the feature is a magnetic structure, a tube of interplanetary magnetic field. While the earlier probe had seen it emerging from lower altitudes, Venus Express had now observed it far out in the planet's tail, showing that these structures continue to much higher altitudes than previously found. As the Venus Express mission neared its end, scientists executed a series of risky aerobraking maneuvers, guiding the probe on daring plunges into the hostile atmosphere, bringing it as low as 130 kilometers above the surface for close-up observations. For this phase, the goal was to create the most friction possible. The spacecraft was oriented so that the face originally attached to its launch rocket, the side best able to withstand the forces and temperatures, entered the atmosphere first. The solar panels were also turned, so their backs faced forward, maximizing the surface area to increase the braking effect. These low passes revealed something unusual, a variability in the atmospheric pressure that suggested the presence of waves. This possible wave-like structure was not expected, and analyzing that data will likely keep scientists busy for some time. Venus Express, which carried a suite of 7 instruments including a magnetometer, a spectrometer, and several cameras to study the atmosphere and space environment, outlived its planned 2-year mission by an additional 7 years before it was finally directed to descend into the planet. The most recent attempt to reach Venus was made by Japan with its Akatsuki probe. Its planned observations are to include cloud and surface imaging with infrared cameras, focusing on Venusian meteorology, including efforts to confirm lightning and search for any current volcanic activity. The probe failed to enter orbit on its first attempt, but JAXA is hopeful that a second attempt will succeed when the probe's heliocentric orbit returns it to Venus very soon. There are many plans afoot for a return to Venus. Even a crewed mission has been studied by various groups. One such study conducted for NASA produced HAVOC, the high-altitude Venus operational concept. It would rely upon 2 spacecraft, an uncrewed atmospheric descent stage and an orbital craft carrying the crew. They would dock, transfer the crew to the descent stage, and then deorbit. Once in the upper atmosphere, a parachute would slow the descent, allowing for the deployment and inflation of a dirigible craft. This airship would then carry the crew at a high altitude, from where they would study the planet below. The return journey would begin with a high-altitude launch back into orbit, where the crew would dock with the orbiter, transfer themselves and their equipment, and then make the journey back to Earth. There, they could potentially dock with an Orion capsule for the final return. Yet another world has long captured our imagination: Mars. Named for the god of war and often the source of humanity's science-fictional demise, we now know this dry, barren planet once flowed with vast reservoirs of water. Its sky was once thick and filled with clouds, holding the tantalizing possibility of life. It remains the only other place in our solar system that humans might one day inhabit. Humanity has dispatched a flotilla of robotic emissaries toward the Red Planet, a kind of technological migration driven not by a desire for conquest, but by an insatiable quest for understanding. The core inquiry revolves around the history of Mars and the potential for life, past or present, to have existed there. This pursuit touches upon one of science's most fundamental questions: whether life as we understand it, even in its most basic microbial form, is a phenomenon unique to Earth. If explorers were to uncover evidence of ancient or even currently surviving microorganisms just beneath the Martian surface, a critical question would emerge. Would this life share a common ancestry with the earliest organisms that developed on our own planet? Or would it represent an entirely separate genesis, having followed its own distinct evolutionary path under different environmental pressures? The possibility that life arises wherever conditions are merely favorable is a profound concept that these missions seek to investigate. Our methodical probing of Mars has been marked by both disappointment and triumph, with a greater number of failures than successes in the early years. The Soviets managed to place 2 orbiters around the planet, while NASA successfully landed its 2 Viking landers. These stationary platforms were equipped with sophisticated analytical laboratories designed specifically to search for indications of microbial activity, yet the results they returned were ultimately ambiguous. Subsequent journeys to Mars continued to face a high risk of failure, but the missions that succeeded were nothing short of extraordinary. These robotic probes have often functioned for many years beyond their planned operational lifetimes, creating a unique situation where Mars is a world inhabited exclusively by machines. Robots meticulously crawl its surface, while a constellation of satellites observes from high above. These instruments have all performed their specialized tasks with remarkable precision, providing an increasingly clear and detailed portrait of the planet and its long history. The scientific strategy coalesced around a central theme, following the water to determine what became of it and where it might persist today. Thanks to specialized instrumentation, missions were able to determine the composition of the polar ice caps. The findings revealed a mixture of frozen carbon dioxide, or CO2 ice, and simple water ice. Characterizing this composition was vital, especially the distribution of frozen water, as a primary goal of all Mars exploration is to trace H2O in all its forms, whether as vapor, solid ice, or, if possible, liquid. The study of ice is crucial because it represents one of the planet's major water reservoirs. The accumulated evidence became conclusive that Mars once held abundant water, with ancient landscapes shaped by lakes, flowing rivers, and perhaps even a vast ocean. To delve deeper, a new generation of rover was conceived, leveraging advancements in robotics, computer processing, and analytical technology. This rover was large, intricate, and heavy, necessitating an entirely new method for a safe arrival on the Martian surface. Engineers devised a system so complex it could not be fully simulated on Earth, a sequence where numerous critical events had to occur perfectly, on schedule, and in the correct order. This innovative solution was the Sky Crane, and the Curiosity rover was its first passenger. The landing process began with a controlled atmospheric entry behind a heat shield, followed by the deployment of a parachute for aerodynamic braking, both fairly standard procedures. The novel part came next, as a rocket-powered Sky Crane detached from the aeroshell. This platform descended gently toward the ground, carefully lowering the rover beneath it on a set of cables. Once the rover's wheels touched the surface, it severed the cables, allowing the Sky Crane to fly away to a safe distance before crashing. The Curiosity rover has proven to be a phenomenal success, navigating the Martian terrain for well over a decade. It has been drilling into rocks, collecting samples, analyzing geological formations, vaporizing targets with a powerful laser, and documenting its journey with high-resolution imagery. Housed within the rover's body is a key instrument package called SAM. This suite contains several different tools that allow scientists to study various gases, helping them understand the chemical composition of the atmosphere, as well as minerals within the rocks and soil. Its primary function is to identify any organic molecules that might be present. The kind of evidence sought are the chemical signatures of past microbial life, not the fossilized bones of larger creatures. If life ever took hold on Mars, the prevailing expectation is that it would have been microscopic. Meanwhile, orbiters like Mars Odyssey and Mars Express have also been contributing to the search from above. After a decade of operation, Mars Express provided a comprehensive global mineralogical map, allowing scientists to know the composition of the surface at any given location, and helping to piece together the planet's history. For the first time, Mars Express also detected methane in the atmosphere. This discovery was highly debated within the scientific community, because methane is a fragile molecule that should be quickly destroyed by solar ultraviolet radiation. Its presence implies that there must be an active source replenishing it, though the origin of that source remains largely a mystery. Later, as Curiosity roamed through Gale Crater, it too found methane, and observed that its concentration varied with the seasons. While methane had been detected from Earth-based telescopes and orbiting spacecraft before, this was the first time a sharp rise and fall in its abundance was measured directly from the surface. This fluctuation strongly suggests that modern Mars is an active world. The central puzzle is the origin of the methane being released. Drawing an analogy with Earth, one leading possibility is a biological source, where subsurface microbial activity consumes certain chemicals and releases methane as a waste product. However, it is impossible to state with certainty that the cause is biological. Therefore, geochemical mechanisms are also considered, in which carbon dioxide and water react at high temperatures and pressures deep underground to produce methane that later seeps into the atmosphere. At present, there is not enough evidence to distinguish whether the organic materials being found are biological or non-biological in origin. Several plausible non-biological explanations exist. For instance, the material could have been delivered to Mars by comets or meteorites, or it could be formed through geological reactions within the rock itself. The excitement of this discovery lies in the renewed hope it offers in the search for chemical traces of life. The organic material has been found. The next great challenge is to determine its source. The latest NASA orbital mission, MAVEN, was launched in November 2013 aboard an Atlas V rocket. It entered orbit 10 months later, designed to seek clues about the evolution of Mars by studying its atmosphere. The Mars Atmosphere and Volatile Evolution mission, known as MAVEN, is dedicated to unraveling one of the solar system's great mysteries: how Mars transformed from a world that was once likely warm and wet into the frigid, arid planet we observe today. The central questions driving the mission are where the planet's ancient water and carbon dioxide have gone. Evidence strongly suggests that water once flowed freely across the Martian surface, perhaps even forming vast oceans. Understanding what caused this profound environmental shift is crucial, and a key element of that puzzle is the planet's atmosphere. Scientists believe Mars once possessed a much thicker atmospheric blanket than it does now, and MAVEN's primary objective is to investigate the processes that could have stripped that protective layer away over geological time, leading to the planet's dramatic climate change. One of the primary mechanisms for this atmospheric erosion is a phenomenon called sputtering. This process begins with the sun, which constantly emits a stream of high-energy photons. When these particles penetrate a planet's atmosphere, they can collide with neutral molecules, forcibly dislodging an electron and transforming the molecule into a charged particle, or an ion. In the presence of a magnetic field, these newly formed ions are captured and begin to spiral along the field lines. The sun itself provides this magnetic field, which is embedded within the solar wind that flows continuously outward through the solar system. As this solar wind and its magnetic field sweep past Mars, they can carry away the ions that have been captured, effectively plucking them from the atmosphere. Other ions, depending on their trajectory, are not swept away but instead accelerate back toward the planet, crashing into the top of the atmosphere. These high-speed collisions act like a cosmic billiard game, flinging other atmospheric atoms and molecules in all directions. Some of these particles are knocked with enough force to escape the planet's gravity entirely, becoming sputtered into space. Over the course of billions of years, this relentless process has gradually thinned the Martian atmosphere and, along with it, removed the planet's surface water. To quantify just how much water Mars has lost, scientists utilize the world's three principal ground-based telescopes for infrared astronomy. This approach allowed them to capture a comprehensive snapshot of an entire Martian hemisphere in a single night of observation. The key to their measurement lies in a heavy isotope of hydrogen called deuterium. Water molecules naturally contain both regular hydrogen and a tiny fraction of deuterium. Because deuterium is heavier, it is less likely to escape into space when atmospheric loss occurs, meaning it tends to remain trapped within the planet's water cycle. By detecting the level of deuterium enrichment in the remaining water vapor, scientists can calculate how much water, and specifically the lighter hydrogen, has been lost over time. The results were clear. Martian water is far more enriched with the deuterated, or heavy, form of water than the oceans on Earth. This finding directly enabled an estimate of the total volume of water Mars has lost since its youth. For a long time, the question of how much water existed on early Mars was poorly defined, with theories ranging from small rivers and occasional rain to planet-spanning oceans. These new findings provided a much clearer picture, indicating that only about 13% of an ancient Martian ocean remains on the planet today, primarily stored as ice in the polar caps. This means a staggering 87% of this original ocean has been lost to space. Such a vast quantity of water would have made early Mars look profoundly different than it does now, with a significant part of its surface submerged. The intriguing question then becomes whether this water could have formed a substantial sea or ocean. The data suggests that it would have, pooling in the northern plains, a vast region of low elevation that is relatively flat compared to the rest of the planet. There, it would have formed an ocean covering approximately 20% of the Martian surface area, a respectable body of water by any standard. This ocean would have reached a maximum depth of around 5,000 feet, or roughly 1 mile deep. While not as deep as the deepest trenches in Earth's oceans, its depth is comparable to the average depth of the Mediterranean Sea. By combining the new estimates for water volume with detailed Martian topography, researchers simulated the ancient ocean and its slow escape into space. As Mars progressively lost its atmosphere over billions of years, it also lost the necessary atmospheric pressure and insulating warmth required to keep water in a liquid state on its surface. This caused the Great Northern Ocean to shrink, its shorelines receding northward. The water that remained eventually condensed and froze over the North and South poles, creating the permanent ice caps that are such prominent features of Mars today. We now have a clearer understanding that Mars was a wet planet for a much longer duration than previously thought. Data from the Curiosity rover had already established a wet period lasting 1.5 billion years, a time frame longer than what was needed for life to emerge on Earth. These more recent findings suggest that the era of liquid water on Mars must have been even more prolonged. It is a fascinating testament to modern science that measurements taken today can reveal so much about conditions 4.5 billion years ago, allowing us to conclude that an ocean covering a fifth of the planet was a reality. This conclusion dramatically opens up the possibilities for Martian habitability and the potential evolution of life. Informed by this expanding knowledge, scientists are now developing the next series of robotic probes destined for Mars. For its part, NASA is building upon its history of success by utilizing hardware and operational systems with a proven track record. The team at JPL and Lockheed Martin has demonstrated its ability to land and operate on the Martian surface, most notably with the Phoenix lander. This experience makes the surface operations for upcoming missions much simpler. One such mission is InSight, a geophysical lander designed to take the vital signs of Mars. Its purpose is to deploy two primary instruments on the surface and leave them to collect data autonomously, without the need for constant ground interaction or repetitive weekly command uploads. InSight will measure the planet's heartbeat by using a highly precise seismometer to detect seismic activity, or Marsquakes. These measurements, analyzed with techniques well established on Earth, will help scientists understand the structure of the crust, mantle, and core. The mission will also take the planet's temperature using a heat flow probe called HP-cubed. This instrument will measure the thermal gradient of the subsurface, revealing how much heat is escaping from the planet's interior over a full Martian year. Finally, InSight will measure Mars's reflexes by carefully tracking how its rotation wobbles in response to the gravitational pull of the Sun. This final experiment, called RISE, will provide critical data about the size and composition of the planet's core. The European Space Agency is also making significant progress with ExoMars, a rover equipped with advanced drilling capabilities that was scheduled for launch by 2018. Its principal objective is to search for microorganisms deep beneath the surface. The novel feature of the ExoMars rover is its mobility, which is not just horizontal but also vertical, allowing it to drill down and explore the subsurface environment. The ability to sample material from beneath the Martian surface represents a critical next step, as it is essential for understanding whether any signs of past life activity remain on Mars. For the very first time, scientific inquiry will extend into the third dimension, the dimension of depth, and it is here that we believe the highest probability exists for making a significant discovery regarding the presence of organic molecules. Mars is an entire world with a complex history, a story captured within its rocks, and our mission is to decipher that narrative and learn what the story of that planet reveals about our own. While the Curiosity rover grinds rock samples into powder to examine their bulk constituents, a future mission would need to operate on a microscopic level. It would require the capability to inspect the rocks for the extremely small and detailed messages they might hold about ancient life that could have once existed there. What is held here is a classic biosignature from Earth, a fossil. On Mars, we are not actually anticipating the discovery of fossils from shells or similar components. The goal, rather, is for our instrumentation to discern the fine-scale layering that can appear in certain types of rock. Within these formations, we can sometimes see alternating layers of dark and light tones, and these subtle bands are telling a story about the environment in which they formed. The question of when NASA will send astronauts to Mars looms large, but progress is steady. Following a liftoff at dawn that marked the dawn of Orion and a new era of American space exploration, the first test flight of the Orion crew capsule was successfully completed. This milestone means the hardware and its associated systems are now ready for mass production, with the components, engineering, and manufacturing all moving forward. NASA is looking back to what has worked in the past and utilizing that proven technology for the future. For instance, the solid rocket booster technology, derived directly from the Space Shuttle program, has been extended and thoroughly tested. The agency's new Space Launch System, or SLS, is steadily approaching fruition. By reusing the Space Shuttle's main engines as the new system's workhorses, NASA is saving billions of dollars and years of research and development. In a key international collaboration, the Europeans are teaming up with NASA to provide the service module for Orion, a component that will allow for long-duration flights into deep space. Meanwhile, autonomous Martian landing systems are in an advanced state of development and are currently being tested, with software and hardware fully integrated for both crewed and uncrewed landings on Mars. And for operations once they arrive, there is the Desert Rats program, which stands for Desert Research and Technology Studies. This is a group of engineers and scientists dedicated to testing new concepts, procedures, and equipment, such as innovative rover designs, to see how they perform in a field environment. The team tests these technologies to ensure that on future human spaceflight missions, we will be able to conduct science as effectively as possible. The program is exploring scenarios that NASA has never attempted before, such as operating 2 human-crewed rovers at the same time. This involves developing complex protocols for how to use these assets simultaneously. There are also interesting challenges one might not immediately consider, like communications. You could potentially have 4 astronauts all talking at the same time to mission control or to the science communication backroom. The entire exercise is run just like a real mission. If you think about an Apollo mission to the moon, you had the astronauts on the surface and the team in mission control, but there was also a science backroom that the public didn't often hear about, from which the astronauts received crucial information and planning. Arizona provides a very good climate for these kinds of analog studies. The state offers vast open plains and a wealth of geological features that are analogous to places on the Moon and on Mars. Long-term space voyages are also being replicated, both on the ground and in orbit aboard the International Space Station. Furthermore, surface habitats, power systems, and methods for food and oxygen supply manufacturing are all on the drawing board. The human flight component of exploration would like to see an experiment where resources found on the surface of Mars, whether from the rocks or the atmosphere, could be used to generate fuel or other parts. This would enable future exploration by, in a sense, cutting the tie to Earth. You would not necessarily have to bring everything with you. You could actually manufacture it on the planet. That is a really exciting additional component that has been explored and analyzed in this work. NASA is not the only organization with its eyes on this prize. The European Space Agency and now the Indian Space Research Organization each have a spacecraft orbiting Mars, and India accomplished this feat on its first attempt. Private enterprise is also hard at work, with groups like Mars 500, Mars One, the Mars Society, Mars Foundation, and the Mars Initiative, to name just a few. These organizations already have volunteers lining up for a one-way trip to the Red Planet. It feels inevitable that we will set foot on Mars in the very near future, and when we do, we will stay and learn her secrets. Perhaps far in the future, we will even be able to alter the atmospheric density through terraforming and return Mars to the world that it once was, awash with oceans and rivers, clouds and rain. Maybe then, some of us could call it home. In the cold, dark expanse of our solar system, far beyond the asteroid belt, lie the giant planets. Some can be seen with the naked eye, while others have been glimpsed only once by a passing probe. We are again sending our cameras to the edge of the solar system, hoping to bring back new insights into the evolution of our world. The Pioneer 10 and 11 spacecraft made the first passage through the asteroid belt, leading the way for the venerable Voyager missions. These 2 remarkable probes conducted a grand tour of the outer solar system before slipping away into the quiet of interstellar space. Jupiter, the first and greatest of the outer planets, with its broiling sky, has received fleeting visits from other missions such as Ulysses, Galileo, and Cassini, each one adding to the mosaic of our understanding of Jupiter and its violent atmosphere. Amy Simon Miller studies the atmospheres of the Jovian planets. She explains that the weather on Jupiter is confined to a rather thin layer, located high up in its atmosphere. Therefore, the tops of the clouds are what we are seeing when we look at the planet. Her team observed that in the southern part of the equatorial region, there are little V-shaped clouds, or chevrons, and they wanted to understand how these features are moving in the atmosphere. The current thinking is that chevrons are simply holes in the clouds, areas where we do not see any bright white clouds. The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, it provided a great deal of coverage of the planet over a long time period. This allowed scientists to put the collected images together and create movies. Using these movies, they observed Rossby waves, which caused north-south meanders in a jet stream. South of the equator, our attention turned to a series of atmospheric features known as hotspots. These are understood to be unique phenomena, driven by a Rossby wave quite similar to one detected previously. The intriguing difference is that this wave, rather than moving north and south, primarily oscillates vertically within the atmosphere. Where the wave moves downward, it pushes air into warmer layers below. This compression and warming effect causes any clouds caught in the downdraft to evaporate, while also preventing new ones from forming. At any given time, Jupiter's atmosphere contains approximately 8 to 10 of these hotspots, distributed at roughly even intervals around the planet. The prevailing belief is that each visible hotspot directly corresponds to one of the downward-moving sections of this deep atmospheric wave. This new finding is particularly exciting because it provides a new framework for re-examining the data from the Galileo probe, allowing us to better understand its findings and place them within the broader context of Jupiter's global climate and atmosphere. The next probe sent to Jupiter with a dedicated mission was Juno. Launched in 2011, the spacecraft reached the gas giant after a 5-year journey. Juno's primary objective was to investigate the planet's deep interior structure and its powerful magnetosphere, helping to refine our understanding of how the planet formed and, by extension, the history of our own solar system. Juno maintains its stability by spinning, much like a propeller with its large solar arrays oriented toward the Sun. This gyroscopic effect keeps it steady, and the constant rotation allows each scientific instrument on board to take its turn observing Jupiter. Its design allows the probe to travel very close to the planet, passing inside the intense radiation belts rather than outside them. The spacecraft follows a polar orbit, and by making small adjustments to the mission's timing, it can progressively map the entire world, capturing repeating stripes of data at different longitudes as Jupiter spins beneath it. This trajectory means Juno is able to see the polar regions in greater detail than any previous spacecraft, but what stands out is how its elliptical path brings it within a few thousand miles of the cloud tops near the equator. Flying over the poles of Jupiter allows for studying the magnetosphere in a different way. A magnetosphere is the sphere of influence created by a magnetic field, a region that extends far out into space, affecting the environment around the planet. Jupiter's magnetosphere is simply vast. If you consider that Jupiter is 10 times the size of Earth, its magnetosphere is then 100 times the size of Jupiter. The Juno probe is also the most distant NASA has ever sent a solar-powered spacecraft. At Jupiter's orbit, sunlight provides 25 times less energy than it does at Earth, a condition that required advanced solar power technology. The solution came in the form of solar cells that were both 50% more efficient and more tolerant to radiation than conventional silicon cells. The craft also houses a radiation-shielded electronics vault, built to protect the delicate electronics from the intense and deadly radiation environment around Jupiter. The probe carries a full set of sensors: a microwave radiometer for atmospheric sounding and composition study, detectors for plasma and energetic particles, a vector magnetometer, a radio and plasma wave experiment, and both ultraviolet and infrared images, plus a color camera called JunoCam. The mission's name is rooted in Roman mythology, which in turn grew from Greek lore. The story tells of the god Jupiter, who would conceal his activities by shrouding himself in a veil of clouds. But his wife, the goddess Juno, possessed her own formidable power, which she used to peer directly through the clouds, to perceive Jupiter's true nature and discover what he was doing. This myth serves as a perfect allegory for the spacecraft's mission, to use its special instruments and unique orbit to see through Jupiter's clouds and understand its true nature, a nature that holds secrets about how the solar system formed and where we all came from. A long-standing feature of the storms of Jupiter is the Great Red Spot. Large enough to swallow the Earth, this storm system has been studied since the 19th century. Then, it was measured at a little over 41,000 kilometers on its long axis. The Voyager 1 and 2 probes measured it at over 23,000 kilometers, and recent observations by the Hubble Space Telescope have the red spot at only 16,500 kilometers long. It seems the rate of shrinkage is increasing, and one day it will probably vanish altogether. Juno will also help confirm the theory that Jupiter was the first of the planets in the solar system to form from the primordial disk of dust and gas some 4.6 billion years ago. The mission is expected to reveal more about the fundamental workings of planets, how they release their internal heat, the nature of the currents flowing deep within them, and the mechanisms that generate their magnetic fields. By learning what Jupiter is made of, we gain a wider understanding of many things. Because Jupiter is the most massive planet in the solar system, it is the body that must be understood in order to grasp the architecture of everything else, including Earth. Juno's year-long mission will end with a deorbit burn and a slow descent into the upper atmosphere, where it will continue to send back scientific data until its destruction. Perhaps the jewel of the solar system is Saturn, with her spectacular rings. All 4 of the outer planets have rings of ice and rock, but Saturn's is the most complicated and, with thousands of ringlets, the most visible. There are several groups of rings, classified A through to G. Some are formed by shepherd moons within the rings and by gravitational tidal effects from others outside, yet some gaps are still unexplained. The spacecraft observing Saturn at this time was Cassini, then on its second extended mission, the Cassini Solstice mission, which was expected to be completed in 2017. It continued to watch the planet-sized storms in the atmosphere. Saturn's great white spots are enormous tempests that tend to erupt roughly once every Saturnian year, a period equivalent to 29 Earth years. The one that emerged in December 2010 began as a small, unassuming white cloud, detected by Cassini's instruments and by observers on the ground. Over the following days, this storm expanded rapidly before being sheared apart by powerful winds at its northern and southern edges. This process stretched the disturbance until it encircled the entire planet. This event was scientifically significant, as it provided the very first opportunity to study a storm of this scale in the infrared. The fortunate timing of having a spacecraft in orbit, combined with excellent ground-based observatories, has allowed for the creation of a comprehensive historical record of Saturn's Great White Spot. This detailed chronicle will provide a crucial baseline for future generations, enabling them to compare their observations when the next one of these colossal storms inevitably erupts. Another of the planet's captivating phenomena is a vast hexagon of clouds that perpetually encircles Saturn's North Pole, a feature that has only recently emerged from the long polar winter into sunlight. For 9 years, the Cassini spacecraft traced a path through the Saturnian system, closely monitoring this geometric curiosity. It is a structure so vast it could contain our own planet more than twice over, formed by a meandering atmospheric jet stream. As spring arrived in the northern hemisphere, the darkness that had shrouded the pole finally lifted, and what lay at the heart of this wonder was revealed to be a colossal hurricane. This view, made possible by Cassini's altered orbit, which carried it over the poles, offers a perspective directly above the planet's northern axis. Inside this storm, winds churn at an astonishing 300 miles per hour, a velocity 4 times greater than that of a terrestrial hurricane. The swirling white clouds that form its core cover an area comparable to the state of Texas. Through the use of specialized filters, scientists can discern the altitude of the cloud tops, where red hues indicate lower layers and green tones reveal higher ones. We refer to it as a Saturnian hurricane because it shares key features with its earthly counterparts, such as a distinct eye and powerful winds. However, it differs in fundamental ways. It remains permanently fixed over the North Pole, and it draws its energy not from a warm ocean below, but from sources deep within the planet's atmosphere, a mystery that continues to puzzle researchers. Another captivating feature of Saturn, first glimpsed by the Pioneer 11 probe in 1979, is its polar auroras. These displays of light, born from the planet's magnetic field, are on a scale far grander than those on Earth. stretching for hundreds of miles above the polar regions. And unlike the bright but fleeting auroras of our own world, which fade after a few hours, those on Saturn can persist for several days at a time. The phenomenon occurs when high-energy particles, accelerated by the Sun, stream into the planet's atmosphere and collide with its gases. This interaction excites the atmospheric gases, causing them to fluoresce and release light at various wavelengths, a process the Hubble Space Telescope has been observing closely. Between 2016 and 2017, the Cassini spacecraft embarked on its final, daring series of orbits. These trajectories sent it plunging into the unexplored territory between the planet's upper atmosphere and the innermost edge of its rings. The primary scientific objectives were to reveal the fundamental internal structure of Saturn, to precisely map its magnetic field, to calculate the mass of the ring system with unprecedented accuracy, and to directly sample particles from a region no probe had ever entered. This final chapter of the mission was a singular opportunity, one that could not be repeated, to observe seasonal variations within the complex system. Uranus remains one of the most mysterious worlds, having been visited just once by a terrestrial spacecraft, Voyager 2. Like the other gas giants, it possesses a ring system, a magnetosphere, and a host of moons. But beyond these basic traits, the planet is an outlier. The images returned by Voyager showed a placid, largely featureless atmosphere, devoid of the dramatic storms and cloud bands seen on other giants. What truly sets Uranus apart is its extreme axial tilt. It orbits the Sun essentially lying on its side, with its poles situated where the equator would be on other worlds. This peculiar orientation is mirrored by its magnetosphere, which is significantly tilted and offset from the planet's center, resulting in a strangely distorted and asymmetrical magnetic field. This, in turn, causes the planet's auroras to appear at locations far removed from its geographic poles. More recent observations from Earth have detected signs of seasonal evolution and a rise in atmospheric activity, which became more apparent as the planet neared its equinox in 2007. Winds on Uranus have been measured reaching speeds of 250 meters per second. While no future missions are currently scheduled, a number of concepts have been proposed, including joint efforts from ESA and NASA. These proposals include orbiters powered by either solar or nuclear sources, and some even feature a probe designed to descend into the planet's atmosphere. Ion propulsion is often considered the ideal choice, as it would enable a heavier and more capable science payload to make the long journey. A potential launch window in 2020 was identified for a 13-year transit to Uranus, but the mission has been classified as a lower priority endeavor, and as such, no funding has been committed. The final planet in our solar system's classical lineup is Neptune, the other ice giant. Its atmosphere is primarily hydrogen and helium, but it is the presence of trace amounts of methane that absorbs red light and gives the world its striking, deep blue appearance. Like Uranus, it has only ever been studied up close on a single occasion, during Voyager's flyby. The detailed photographs captured during that encounter unveiled a dynamic atmosphere marked by wispy white clouds and a colossal storm system driven by supersonic winds. The storm itself was observed to circle the planet in just 18 hours, while also rotating on its own axis over a period of 16 days. Voyager's observations also uncovered a faint ring system and brought the total count of confirmed moons to 14. Its largest moon, Triton, is a particularly fascinating world, thought to be a captured object that originated in the distant Kuiper Belt. The spacecraft also found that Neptune's magnetic field, much like that of Uranus, is significantly offset from its center and tilted at a sharp angle. Both of these ice giants remain poorly understood due to the scarcity of direct observation. NASA has explored various mission concepts for a return to Neptune, including an orbiter and probe combination modeled after the successful Cassini-Huygens mission. Yet, owing to budgetary limitations and competing priorities, none of these proposals have moved forward to approval. The Voyager mission to the outer solar system stands as a journey of a lifetime for those involved. The encounter with Triton, the final world on its grand tour, was described as a moment of immense satisfaction for the scientific community. When the New Horizons mission was first conceived, constructed, and sent on its way, Pluto held the status of the 9th planet. Its subsequent reclassification to a dwarf planet did nothing to diminish the scientific imperative to investigate this distant world. One of the driving principles of planetary science, as articulated by the team, is the fundamental need to travel to these destinations to get the high-resolution data needed to truly see what is happening. New Horizons was hailed as the first of a new class of spacecraft, one designed with a laser-like focus on a specific objective. The mission's philosophy was one of disciplined focus. The team decided against trying to answer every possible question, concentrating instead on the most basic inquiries. What are the appearances of Pluto and its moon Charon, and what materials are they composed of? The scientific instruments aboard the probe were engineered specifically to address these core objectives. To accomplish its long journey in a reasonable time frame, New Horizons was designed to be lightweight and was launched atop one of the most powerful rockets available. This combination allowed it to shatter all prior speed records for a departing spacecraft, leaving Earth on a solar escape trajectory at an incredible 16.26 kilometers per second. This remarkable velocity effectively reduced the travel time to Pluto by 3 years. The mission marked humanity's first visit to the dwarf planet Pluto and its largest moon, Charon. Pluto's planetary status was revised because it did not meet one of the 3 modern criteria for a full-fledged planet. Specifically, it has not cleared its orbital path of other objects. Instead, it coexists with numerous other bodies in the Kuiper Belt, a region that is home to other dwarf planets as well. The stunning images returned from the spacecraft's closest approach to Pluto revealed a complex and surprisingly active world. It remains a rich source of scientific data, holding countless questions and, hopefully, the answers that will illuminate the origins and evolutionary history of our entire solar system. After its historic encounter with Pluto, the New Horizons spacecraft ventured onward toward the unknowns of the Kuiper Belt. This vast, donut-shaped realm at the solar system's edge is home to its most numerous objects, the ice dwarf planets. It can be imagined as a far grander version of the asteroid belt, containing hundreds of times more bodies. The probe's extended mission involves visiting some of these distant worlds. Mission planners noted that once the spacecraft's trajectory was known, they could calculate the precise fuel needed to reach these targets. An intriguing detail emerged from these calculations. They might need to fire the engines specifically to avoid a collision with one object, a testament to the careful navigation required in this crowded space. These particular bodies, known as cold classicals, are especially compelling. They are seen as pristine fossils, preserved in their original state for some 4.5 billion years. What they will look like remains a complete mystery, and New Horizons is scheduled to continue its exploration of this remote frontier until 2026. Our solar system contains a multitude of worlds, with most residing far beyond the asteroid belt. Here, orbiting the gas giants, are moons that are each a unique and enigmatic realm. Some may hide oceans of water, others vent geysers of sulfur, and a few possess unusual atmospheres of plastic-like compounds. Many of these bodies at the solar system's outer rim are only now coming into focus, and all of them merit deeper investigation. Currently making its way toward the Jovian system is the scientific probe Juno. It represents the first dedicated orbiter to visit Jupiter since the Galileo mission concluded in 2003. Juno's objective is to enter a highly elliptical orbit over the planet's poles and study it in unprecedented detail. While several other probes have passed through the system on their way to other destinations, providing valuable data on Jupiter and its moons, Juno's focus is singular. Jupiter, the largest planet in our solar system, is known to have at least 67 satellites. The majority are irregularly shaped masses of rock, likely captured asteroids like Amalthea, held in place by the planet's immense gravitational field. 4 of its satellites, however, are major worlds in their own right. These are the Galilean moons, each one large and dense enough for its own gravity to have formed it into a sphere. They bear the name of the great Italian astronomer Galileo Galilei, who first observed them in 1610. The innermost of these worlds is Io. Though slightly larger than our own moon, it is the smallest of the 4. Its proximity to Jupiter subjects it to intense gravitational forces, which are the source of its violent and active geology. The moon is covered with over 400 active volcanoes, vast lava flows, and enormous plumes of sulfur that can rise 300 kilometers above the surface. Io is also the most dense and the driest of the Galilean moons. Scientists believe it is composed primarily of silicate rock surrounding a molten core of either iron or iron sulfide. Its surface is a landscape of extensive plains coated in sulfur and sulfur dioxide frost. This surface is geologically young, which explains the complete absence of impact craters. Any that form are quickly buried by fresh volcanic material. The immense internal energy driving this hyperactive moon comes from the relentless tidal forces exerted by Jupiter on one side and the other large moons orbiting farther out. Just slightly smaller than Earth's moon is Europa, a world with an icy crust that is thought to conceal a global, salty ocean, one that might be capable of supporting life. It, too, shows signs of activity, with geysers that eject material from below into space. The belief in Europa's ocean arises from a combination of evidence. Information gathered by ground-based telescopes has been synthesized with data from spacecraft that have flown past the moon. These probes collected measurements of the surface, provided clues about the interior structure, and mapped the magnetic field around Europa. The convergence of these datasets gives scientists a high degree of confidence that a global ocean of liquid H2O exists there today and has been present for much of the solar system's history. This is what makes Europa a true game changer. It is located very far from the Sun, yet it possesses a liquid water ocean. The reason for this is the tidal tug and pull from its orbit around Jupiter, which causes the entire moon to flex. This constant flexing generates tidal energy, which transforms into mechanical energy and then into friction and heat. That internal heat helps maintain the liquid ocean beneath the icy shell. Beyond simply keeping the water liquid, it's thought that this same tidal energy could also facilitate interaction between the ocean and the rocks of Europa's seafloor. This process might even give rise to features like hydrothermal vents, which could supply not only the chemical building blocks for life, but also the very energy that life requires. Consequently, Europa is considered the most probable place in our solar system to find life today. We know that on Earth, life is found everywhere that water exists. The profound question, then, is whether Europa also has the right ingredients to support life. The reddish material seen on its surface suggests something is happening, pointing to a world that is presently alive and geologically active. It is an environment that could be habitable, and scientists feel an imperative to go back and find out. The Europa Clipper mission was designed specifically for this purpose, to send a spacecraft and a suite of advanced instruments all the way from planet Earth to Jupiter. Earlier mission concepts had envisioned a craft that would orbit Europa directly. However, Europa is bathed in the intense radiation emanating from Jupiter, and any mission in its immediate vicinity would be disabled very quickly. Instead, the current plan involves a mission that will orbit Jupiter and make dozens of close flybys of Europa, dipping into the high radiation zone only briefly before retreating. This strategy allows the mission to last for many years, providing ample time to collect and transmit a vast quantity of data. As Europa orbits Jupiter, it flexes, and the spacecraft could measure the resulting gravitational changes by encountering the moon at different points in its orbit. On a typical flyby, remote sensing instruments would be activated to image the surface and analyze it with spectroscopy. This process would be repeated many times until a global understanding of Europa is achieved. Furthermore, images from the Hubble Space Telescope suggest that Europa might be venting plumes of water high into space. If this is true, the spacecraft could fly through those plumes and sample the material directly. This would allow scientists to understand the composition of Europa's interior and assess whether its hidden ocean has the potential to harbour life. To understand the mechanics of how nutrients might be replenished in a subsurface ocean, a suite of advanced instruments will be necessary. Europa holds a place of profound importance in our quest to know if we are alone in the universe. The discovery of life there would almost certainly point to an origin entirely separate from life on Earth. A remarkable feature of our time is that for the first time in human history, we possess the technology and capability to potentially answer this fundamental question, and we have a clear destination in mind: Jupiter's ocean world. The Europa Clipper mission has now moved beyond its initial development and strategy phases, securing the necessary funding to proceed. An invitation has been extended to the European Space Agency to contribute an additional probe that would travel alongside Clipper, much like the Cassini-Huygens mission, with the objective of either landing or impacting the Moon's surface. The primary plan for the Europa Clipper involves executing 45 flybys of Europa, with altitudes ranging from as high as 2,700 kilometers down to a close approach of just 25 kilometers. A proposed launch is targeted for 2025. If it utilizes NASA's new Space Launch System, a powerful heavy-lift rocket, the journey to Jupiter would take under 2 years. The alternative would involve a much longer flight of 6.5 years. Another of Jupiter's icy moons, and the largest in our entire solar system, is Ganymede. Its structure is a mix of silicate rock and water ice. Its surface tells a story of a dynamic history, heavily marked by impact craters alongside vast regions shaped by tectonic activity. A tenuous atmosphere composed of oxygen, possibly some ozone, and atomic hydrogen surrounds the Moon. Deep inside, Ganymede is thought to have a liquid, iron-rich outer core and a global internal ocean that could hold more water than all of Earth's oceans combined. The most recent models of its interior suggest a fascinating structure of alternating layers of water and ice, sometimes described as a club sandwich. Uniquely, Ganymede is the only moon known to possess its own magnetic field. While this field is embedded within and largely overpowered by Jupiter's immense magnetosphere, there are still signs of auroral activity on the Moon. Ganymede is also slated to be the final destination for the Jupiter Icy Moons Explorer, or JUICE. This mission, designated by the European Space Agency, will study 3 of the Jovian moons. It is scheduled for a 2022 launch from Europe's spaceport in Kourou, French Guiana, aboard an Ariane 5 rocket. After arriving at Jupiter in 2030, it will spend a minimum of 3 years conducting detailed observations. Its itinerary includes a visit to Callisto, the solar system's most heavily cratered body, and it will also perform 2 flybys of Europa. Callisto is the 4th of the major Jovian moons and the most distant from Jupiter, a position that places it outside the planet's primary radiation belt. In contrast to its sibling moons, Callisto has an extremely thin atmosphere of carbon dioxide and molecular oxygen and experiences significantly lower radiation levels. The moon's composition is a blend of silicate rock and water ice, and like its neighbors, it may also conceal a subsurface ocean. Because of its more benign environment, it is often considered the most viable location for a potential future human base in the Jovian system. The Saturnian system is home to 62 confirmed orbiting satellites, a great many of which are less than 50 kilometers in diameter. The larger, spherical moons, such as Mimas, Enceladus, Tethys, Dione, and Rhea, are constructed predominantly of water ice with a smaller fraction of rock. Among these, Enceladus stands out. It is covered in a shell of ice that hides a subsurface ocean, particularly at its southern pole. This southern region is geologically active, with geysers of gas having been observed erupting into space. This activity is thought to be driven by tidal heating, a result of its orbital resonance with Dione and Rhea, and could sustain a liquid ocean warmed by internal radioactive decay. Yet, the undisputed prize of Saturn's system is Titan. It is the only moon in our solar system with a dense atmosphere, and apart from Earth, it is the only celestial body known to have stable bodies of liquid on its surface. Titan is immense, larger than the planet Mercury and even our own moon. It was here that the Cassini mission successfully deposited the Huygens probe onto its surface back in 2005. As Saturn's largest moon and the second largest in the solar system, Titan's substantial atmosphere makes it unique. Scientists note that in some ways, its atmosphere is quite similar to Earth's, being composed mostly of nitrogen. However, in other respects, it is profoundly different. Methane is its next most abundant gas, and it plays a role analogous to water vapor in Earth's atmosphere. It evaporates from the surface, forms clouds, and then precipitates back down. This cycle creates the lakes we can now see at Titan's North Pole, which contain not just methane but also ethane, propane, and a variety of other complex chemicals. We also observe vast dune fields near the equator. These are not made of silicates as they are on Earth, but are instead formed from organic substances, essentially plastics, which have sedimented out of the atmosphere and are then sculpted by winds into dunes, just as we would see in a desert on our own planet. By analyzing the atmosphere, researchers can detect which molecules are present. They see all the molecules previously identified by Voyager, but they are also able to search for new ones. Buried within the signals of more common molecular species, a very small spike was detected, which was attributed to a species never seen before. This molecule was identified as propylene. The discovery of propylene on Titan is particularly exciting. For one, it completes a chemical family that had a missing link dating back 32 years to the Voyager encounters. It also demonstrates that there is much more yet to be discovered within Titan's complex atmosphere. Some scientists believe that Titan may be similar to the prebiotic Earth of long ago, when molecules were forming the very basis of life. It remains unknown what might be found on Titan if we send future spacecraft equipped with new, more sensitive instruments. There is a possibility that some of the molecules on Titan could be similar to the foundational chemistry of life on Earth. NASA is currently preparing a new probe to follow in the path of Cassini, a mission called the Titan-Saturn System mission. While Cassini was able to observe the lakes and get a sense of their general composition, it could not determine anything about the organic molecules dissolved within them. The Titan-Saturn System mission is conceived as a 3-in-1 endeavor, featuring an orbiter for Titan, a balloon that will float through its atmosphere, and a lander designed to splash down into one of the northern lakes. This mission will be able to go directly into a lake, sample the liquid, and see precisely what organic molecules are present. The Titan-Saturn System mission will also travel to Enceladus, the much smaller moon, 1,000 times smaller than Titan, which has what are essentially geysers, spewing material from its interior outward. This presents an opportunity to see if there might be molecules that would indicate life has actually formed within the source region of these plumes. The geysers are known to contain water ice, and there is strong suspicion that liquid water exists in the region where they originate. We know organic molecules are there because they have been detected. The data gathered by Cassini highlights a critical need to follow up on its discoveries swiftly. A generation of scientists, now expertly trained through the Cassini-Huygens mission, stands ready to deploy new instruments and capabilities at Titan and Enceladus. They are poised to answer the profound questions Cassini left behind. Maintaining this continuity of expertise and scientific passion is vital, yet it presents a significant challenge for outer solar system exploration, where travel times are exceptionally long. The proposed Titan-Saturn System mission represents a concept akin to something from the imagination of Jules Verne. It is a mode of planetary exploration entirely without precedent anywhere in our solar system, and one that is uniquely possible at Titan. This mission promises to engage our deepest sense of wonder as it investigates this captivating world. It is designed to drift upon the surface of an alien lake and float through the dense atmosphere, all while an orbiter maps the entire moon. In every respect, it embodies the truest spirit of exploration, the unveiling of a completely new world. The planet Uranus is accompanied by 27 documented moons, which are organized into 3 distinct categories: 13 inner moons, 5 major moons, and 9 irregulars. Our entire knowledge of these distant worlds comes from a single flyby accomplished by Voyager 2, leaving a great deal yet to be discovered. The primary moons, listed in order of their distance from the planet, are Miranda, Ariel, Umbriel, Titania, and Oberon. 4 of these worlds show evidence of internal geological processes, including volcanism and the formation of vast canyons on their surfaces. Miranda, the most diminutive of Uranus's spherical moons, is also one of the smallest known bodies in the solar system to have achieved a round shape under its own gravity. What is particularly strange is that it also possesses the tallest cliffs yet discovered anywhere. These are thought to be composed of a roughly equal mixture of rock and ice. Ariel's surface, likely made of ice, is heavily fractured by a network of canyons, ridges, and scarps. Umbriel is similarly believed to be a composite of rock and ice, but its surface is the darkest among its siblings and is saturated with craters. Evidence suggests this moon underwent some form of surface heating that erased its most ancient features. Titania is the largest of Uranus's satellites and shares a similar composition. Its own history of heavy cratering has been partially obscured by surface alterations from a past heating event. Much like its sister moon Umbriel, Titania might possess an extremely thin atmosphere, as detections of carbon dioxide and water ice have been made on its surface. Oberon, the most distant of the major spherical moons, appears compositionally similar to the others, a world of ice and rock that is heavily cratered. Its surface displays numerous fault scarps and troughs resulting from crustal movements. At present, there are no missions planned to return to these enigmatic worlds. Neptune possesses 14 known moons, which are divided into two classifications: the regulars and the irregulars. The 7 inner moons follow conventional orbits, while the other 7, including the largest moon Triton, travel in paths that are either eccentric, highly inclined, or retrograde. Triton's motion is particularly notable, as it orbits in the opposite direction of Neptune's own rotation. This leads scientists to believe it was likely an independent object captured by Neptune's powerful gravity during the solar system's early history. Triton has a tenuous atmosphere that can form clouds and haze, and it remains the only one of Neptune's moons to have been observed in detail during the Voyager flyby. Beyond its moons, Neptune exerts a profound influence at the edge of the solar system. The planets originally formed from a vast disk of dust that encircled our young sun billions of years ago, and remnants of that disk persist today. These include the rocky asteroid belt, shaped by Jupiter's gravity, and a much larger cloud of icy debris beyond Neptune. Neptune's presence carves a distinct ring-like structure into this dust cloud, creating a noticeable gap where the planet itself orbits. This gap should theoretically make Neptune's location easy to pinpoint from a great distance, even when the planet itself is too faint to be seen directly. Supercomputer simulations conducted by Mark Kuchner and his colleague have allowed them to visualize what the dust in our solar system might have looked like when it was much younger. This work effectively allows them to journey back in time to observe how the distant appearance of our solar system has evolved. When they factored in the effects of collisions between dust particles, the results were astonishing. These dust collisions fundamentally altered Neptune's gravitational signature. The clear gap in the ring structure gradually disappears over billions of years as Neptune's gravity shepherds the dust cloud into a more defined outer ring, which we now recognize as the Kuiper Belt. The New Horizons spacecraft is currently exploring this very region. Its first major objective was a flyby of the perplexing Pluto and its moon, Charon. Charon stands as the largest of Pluto's 5 known moons. The other 4 satellites orbit erratically around the combined Pluto-Charon system. The oddly shaped moons, Nix and Hydra, are prime examples, with their irregular forms contributing to their tumbling, unpredictable orbital motions. An image of Hydra, captured by New Horizons from a distance of nearly 650,000 kilometers, clearly reveals its non-spherical shape. Pluto was the very first of these trans-Neptunian objects to be found. It was initially considered the 9th planet, but for a long time it was seen as something of an anomaly, a small, solitary object at the solar system's fringe. The subsequent discovery of many other similar worlds has led to a re-evaluation, establishing this as almost a third major category of celestial body. The New Horizons flyby represented the first time humanity could study a brand new type of object up close, a world that has been slowly forming for billions of years, providing invaluable insight into the nature of the outer solar system. Pluto is the first of the Kuiper Belt objects, or KBOs, to be viewed in high resolution, but many other dwarf planets in this region await detailed investigation. Among them are Eris, which is nearly the size of Mercury, and Quaoar, the first KBO to be discovered after Pluto. The most extreme orbit belongs to Sedna, which follows an 11,000-year elliptical path that carries it all the way to the icy Oort cloud at the solar system's absolute edge. One day, this distant Oort cloud will surely become humanity's next great frontier. Our solar system is an expanse of unimaginable scale. The distance from our own star, the Sun, to Earth is close to 150 million kilometers, a standard of measure known as 1 astronomical unit. By comparison, Jupiter is 5.2 AU away, while Pluto can be as far as 48 AU. Yet the solar system's influence extends much farther than this, deep into interstellar space. Human beings are not yet capable of traversing such immense distances. However, we can and do dispatch robotic probes and explorers in our stead, and the discoveries they return are nothing short of astounding. The ion-propelled Dawn spacecraft is one of these remarkable emissaries, having rendezvoused with 2 distinct objects in the asteroid belt during its multi-year mission. The Dawn mission, part of NASA's Discovery program, was launched in September of 2007. It followed a long and intricate trajectory from Earth, using a Mars flyby for a gravity assist on its way to the asteroid belt. Its first destination was Vesta, where it spent a full year orbiting the small, rocky body. During this time, it meticulously mapped the surface, determined its overall composition, and studied the geological features of Vesta. After completing its work, Dawn departed Vesta's gravitational field and journeyed for another 3 years to reach the dwarf planet Ceres. Before the spacecraft's arrival at Ceres, scientists were anticipating an inert, rocky world. Instead, what Dawn discovered was a place of profound mystery and surprise. For more than 2 years now, the Dawn spacecraft has maintained its orbit around Ceres, providing us with a continuous stream of fascinating views from an alien world. Among the most compelling discoveries are the mysterious bright spots on the surface, which appear to be salt deposits left by some form of subterranean activity. Compelling support for this theory can be found at another prominent feature, the luminous mountain designated Ahuna Mons. Scientists explained that after conducting a detailed analysis of the mountain's shape, they compared it with what is known about volcanic constructs. What they found was that the form of Ahuna Mons is remarkably similar to that of a volcanic dome, the kind that is built by the eruption of a very viscous material. When they first observed Ahuna Mons, they noted its considerable height and steep slopes, a shape that reminded them of certain formations in the solar system, including on Earth and Mars, where domes have been formed by the volcanic activity of very slow-moving, thick material. The complication, however, is that temperatures on Ceres are so intensely cold that the type of magma common to Earth and Mars simply cannot exist there. This led the team to conclude that the flowing material on Ceres had to be composed mostly of a very salty water, a brine that could flow at the dwarf planet's low temperatures. Once this material was pushed out onto the surface, it would freeze solid, gradually building the steep-sided dome we see today. Ahuna Mons is unique. There is no other place in the solar system known to have a structure that matches it, and it must have been formed by cryovolcanic activity. Adding to this picture, scientists at the German Aerospace Center have used stereo images to create a comprehensive global digital terrain map of the dwarf planet. This work yielded another surprise when a study published by lead author Norbert Schurghofer revealed permanently shadowed regions at the North Pole. These areas are expected to be cold enough to accumulate water ice over long spans of time, making it likely that future spacecraft visiting Ceres will find deposits of freshwater ice there. Right now, we are not only learning about the dwarf planet Ceres, but also about planets and small bodies in the outer solar system, like Pluto and its moons. We find ourselves in a new phase of space exploration, learning about a new class of object. What we are seeing is that these worlds are surprisingly dynamic, with features that suggest recent activity on their surfaces. This observation tells us that Ceres was active in the recent past and might even be active today, underscoring the importance of sending a spacecraft to a dwarf planet for a close look at its surface, where we continue to learn new and unexpected things. Dawn is now orbiting just 386 kilometers above Ceres, which is closer than the International Space Station is to Earth, and it will continue to return spectacular views. One of the key technologies that made Dawn such a success was its ion drive. Ion propulsion allows us to undertake missions which would be impossible without it. While there have been previous missions and tests to validate the basic technology, Dawn has now made it a reality for deep space exploration. It remains the only spacecraft in more than 58 years of space exploration to orbit 2 separate extraterrestrial destinations, the last uncharted worlds in the inner solar system. This technology not only allows us to get to these distant bodies, but once we are in orbit, we can maneuver extensively in order to get the best possible science from the mission. Our second deep space emissary has only recently arrived at its destination, the giant planet Jupiter. The Juno probe is our fastest to date, reaching a top speed of 265,000 kilometers an hour, or 73.6 kilometers a second. It has traveled for almost 5 years to reach its target, and now orbits the poles of the largest planet in the solar system. Juno is the fastest spacecraft ever to venture into the outer solar system, the first to orbit pole to pole around Jupiter, and the most heavily shielded spacecraft that we have ever launched. The mission is designed to essentially wrap Jupiter in a dense net of observations, completely covering the sphere. To do that, a polar orbit is necessary, one that passes over the North Pole, along a line of longitude, and over the South Pole. This will be done over the 37 orbits of the nominal mission, and by the time it is complete, we will have orbits separated in longitude by about every 12 degrees, allowing us to completely cover the sphere. Fundamentally, the interior of Jupiter is nearly unexplored. What we see when we look at Jupiter, and all the amazing things we have discovered, is about the moons that orbit the planet, its atmosphere, the enormous weather systems, the Great Red Spot, and the belts and zones that create stripes across the planet. All of this is incredibly interesting, but it is also skin deep. When we look at Jupiter, we are going only 1% or 2% of the way down into the planet. Everything else about Jupiter, its deep interior, is nearly completely unknown. To peer beyond the veil, the suite of instruments on board Juno includes a gravity radio science system, plasma and energetic particle detectors, ultraviolet and infrared spectrometers, and a vector magnetometer. A magnetometer is best thought of as a fancy compass. Unlike a compass that just records the direction of the magnetic field, this instrument tells you both what direction the field is in and what its magnitude is, and it can measure that very, very accurately, to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built at Goddard Space Flight Center, following designs developed by Mario Acuna years ago. This instrument is between 1 and 2 orders of magnitude more accurate than anything that has flown to Jupiter before. Part of that precision is the result of the star cameras that we are able to fly with our sensors, which allow us to determine the absolute orientation of these sensors in space. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. To this end, we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So, a special structure was designed, called a magnetometer optical bench. It is about a square foot in size and is made of a carbon silicon carbide material. This composite is almost impossible to machine, but once it is fabricated and the sensors are assembled, they act as one. This is one of the reasons why we can achieve much higher accuracy than has ever been attempted before. Studying the magnetosphere of Jupiter is a prime objective, a modern pursuit of a phenomenon, magnetic fields, that has been a curiosity for thousands of years. The source of a planet's magnetic field is now understood to be a process known as dynamo action, involving the convective motion of an electrically conducting fluid deep within its core. While modern satellites allow us to map Earth's own magnetic field with remarkable precision, a fundamental obstacle remains. We cannot peer directly through the magnetized crust just beneath the surface. The gas giant Jupiter, however, presents a unique opportunity. Composed primarily of hydrogen and helium, it has no solid crust to block our view of the dynamo operating deep within. The great promise of the Juno mission is therefore the chance to image, for the first time, the magnetic field right at the surface of the dynamo itself, a feat impossible to achieve on our own world. Jupiter also possesses the solar system's most powerful magnetic field, creating a magnetosphere of colossal proportions. If this vast magnetic bubble was somehow visible to us in the night sky, its apparent size would be comparable to that of the full moon. This structure is so expansive that data from the Voyager program revealed its magnetic tail. The portion stretched away from the Sun extends all the way to the orbit of Saturn, and in all likelihood, even farther. It remains one of the largest, yet entirely invisible, features in our solar system. A magnetic field of such strength inevitably traps a great deal of radiation, posing a significant challenge for the Juno spacecraft. The mission must contend with 2 forms of radiation exposure. One is instantaneous exposure, or flux, which occurs during a single pass through the radiation belts. The other is the cumulative effect, or dose, which builds up from repeated flights through these hazardous zones. Early in its mission, Juno's trajectory keeps it relatively close to the planet, flying beneath a flattened, donut-shaped radiation belt. But as the mission progresses, the orbits pass more frequently through the belts, causing radiation levels to intensify with each pass. More than 80% of the mission's total radiation exposure is expected to occur during its final half. For scientists, the ultimate reward is the chance to look down and capture the first clear, unobstructed picture of a magnetic field at the very surface of the dynamo where it is born. The prospect of being the first people in history to witness this fundamental planetary engine with such clarity is an incredible one. Our emissary to the ringed planet, Cassini, is now in its final year of operation. Its outstanding performance has included deploying a probe onto the Moon Titan and conducting extensive surveys of Saturn and its moons. The mission even adapted its flight plan to fly directly through the remarkable plumes of water vapor that were discovered gushing into the void of space from the Moon Enceladus. While Cassini was not originally equipped to search for life, its powerful instruments can be used to assess the Moon's habitability by looking for conditions suitable for life. Enceladus itself is a tiny yet captivating world, distinguished by a plume of material jetting out from its south pole. This plume consists mainly of water that freezes into ice particles as it is ejected, with its source appearing to be 4 large fractures nicknamed the tiger stripes. The fundamental requirements for life as we know it are threefold: water, chemistry, and energy, and current evidence suggests that Enceladus may possess all three. Cassini has detected not only salts but, crucially, organic molecules such as methane, carbon dioxide, and ammonia. Another key substance the spacecraft can search for is molecular hydrogen. The presence of this molecule could point to hydrothermal activity on the floor of Enceladus's ocean, a critical piece of information as we pursue the ultimate question of whether life truly exists on this small, distant moon. In its final phase, NASA's Cassini mission has embarked on a daring set of ring-grazing orbits, skimming just past the outside edge of Saturn's primary rings. These maneuvers bring the spacecraft closer to the rings than at any point since its arrival over 12 years ago. This proximity will allow for the most detailed study of the rings ever conducted and provide unprecedented views of the small moons orbiting nearby. Even more audacious orbits will take Cassini through the F-ring, Saturn's outermost and most dynamic ring, which contains one core ring and a surrounding spiral strand. Later this year, Cassini will make its final orbit and plunge into the Saturnian atmosphere, ending more than 11 years of extraordinary scientific observations. Having journeyed for over 10 years across 5.5 billion kilometers, the New Horizons spacecraft serves as our envoy to the solar system's distant frontiers. In a swift flyby, New Horizons scanned Pluto and its largest moon, Charon. This brief encounter gathered gigabytes of data, which the probe then spent months transmitting back to Earth. The resulting close-up details of Pluto's terrain generated a great many questions, revealing a world far more geologically complex and active than anyone had anticipated. Its landscapes are shaped by solid nitrogen ice, which forms a variety of captivating and colorful textures and landscapes. New Horizons also captured a high-resolution, enhanced color image of Charon just before its point of closest approach. The moon's color palette is less varied than Pluto's, but one feature that stands out is its reddish north polar region, a feature informally known as Mordor Macula. Following this successful flyby, the mission was granted an extension to include a second Kuiper Belt encounter. New Horizons is now on a trajectory to fly past 2014 MU-69, a Kuiper Belt object located approximately 1.6 billion kilometers beyond Pluto, with an expected arrival in January 2019. As one mission's story draws to a close, another is just beginning. Bepi Colombo, Europe's first mission to Mercury, is currently undergoing rigorous testing at ESA's European Space Research and Technology Centre in the Netherlands. The mission is designed as a composite spacecraft stack, comprising several distinct components. In addition to its 2 scientific orbiters, the stack includes the Mercury Transfer Module, equipped with a solar electric propulsion engine for the journey. This transfer module is what brings the 2 spacecraft to Mercury, propelled by 4 thrusters fed by 3 xenon tanks. Upon arrival, this propulsion unit will be jettisoned, leaving only the 2 orbiters to begin their work. These 2 spacecraft are ESA's Bepi Colombo and the JAXA Magnetospheric Orbiter. Mercury holds the distinction of being the closest planet to the Sunday. Yet despite surface temperatures that can reach around 500 degrees Celsius, the previous NASA Messenger mission uncovered compelling evidence for the existence of ice at the planet's north pole. One of the spacecraft is provided by ESA. It is a planetary orbiter for Mercury, known as the MPO, and its focus is on studying the planet itself. The scientific objectives for the planet Mercury involve detailed remote sensing to characterize its surface, including its vast craters, and to understand the composition of both its crust and its deep interior. This endeavor involves a second spacecraft, the Mercury Magnetospheric Orbiter, which is a contribution from the Japanese Space Agency designed to concentrate specifically on the planet's surrounding environment. The earlier Messenger mission had already returned some surprising findings from the solar system's smallest planet, revealing a greater abundance of volatile chemical elements at the surface than had been anticipated. While Messenger's observations were largely confined to the North Polar region, Bepi-Colombo is equipped with instruments that will provide comprehensive coverage of the entire planet and map its gravitational field. One of the most compelling aspects of Mercury is that it is the only terrestrial planet other than Earth to possess a magnetic dipole field. A primary goal is therefore to comprehend how this magnetic field interacts with the Sun, as this knowledge is profoundly important for us. It offers a simpler model that could yield insights into how Earth's own magnetic field engages with solar phenomena. The interaction with the solar wind affects the many satellites orbiting our homeworld, so any clues gleaned from processes at Mercury could have practical applications for Earth. After experiencing delays due to minor hardware issues, Bepi-Colombo's launch was rescheduled for late 2018, with an arrival at Mercury projected for 2025. Elsewhere in the solar system, NASA has officially greenlit the Europa Clipper mission, which is now moving forward with the selection of its scientific instrument payload. The spacecraft is slated for a launch in the early 2022s, its journey directed toward Jupiter's moon Europa, which is widely believed to harbor a vast liquid water ocean beneath its frozen shell. Europa's close and rapid orbit around Jupiter subjects the moon to immense gravitational forces, causing it to constantly stretch and contract. This process generates significant mechanical heat within its core, providing the necessary energy to sustain its subsurface ocean in a liquid state. Furthermore, analysis of surface features suggests that the movement of ice, analogous to glacial flows on Earth, might create conditions for liquid water lakes to form much closer to the surface, presenting yet another intriguing location in the search for life. For more than half a century, a steady stream of robotic explorers has been sent to Mars, studying the planet from orbit to map its terrain and landing on the surface to probe its resources and understand its environment. This long campaign of reconnaissance has paved the way for the next generation of robotic missions, which are preparing to establish a foothold for the eventual arrival of human explorers on the Red Planet. The exploration of this distant and enigmatic world has been both a challenging and a deeply rewarding pursuit. The European Space Agency's most recent contribution is the ExoMars Trace Gas Orbiter, tasked with identifying the source of methane in the Martian atmosphere. Its companion landing craft, the Schiaparelli lander, unfortunately failed during its descent and was lost. Having been successfully captured by Mars's gravity, the ExoMars orbiter then commenced the difficult task of settling into a circular orbit without relying on its engines. This required a technique known as aerobraking, where the spacecraft repeatedly dipped into the upper atmosphere, using the atmospheric drag to gradually reduce its speed. This was the first time ESA had employed this fuel-saving method for a mission at Mars. The procedure demanded considerable safety margins to ensure the spacecraft would remain unharmed, even if it encountered unexpectedly dense pockets of atmosphere at its flight altitude. The entire aerobraking process took over a year to complete and was made more complex by the variable nature of the Martian atmosphere. The Trace Gas Orbiter is focused on detecting active processes currently happening on Mars, and the presence of life is one potential explanation for the methane it seeks. Mission scientists have described the work ahead as a careful process of scientific deduction, piecing together evidence to determine whether biological or geological activity is the responsible source. In the meantime, planning is well underway for the ExoMars 2020 mission. The rover's final design is approaching completion, and scientists have narrowed down the potential landing sites to two candidates, Oxyaplanum and Marth Vallis. Both locations were chosen because they show clear evidence of having hosted abundant water early in the planet's history, a key ingredient for life. The primary criterion is that the landing site must be ancient, dating back 3.9 to 3 billion years, a period when conditions on Mars are thought to have been similar to those on early Earth when life first emerged. The The second requirement is for a site that contained liquid water for hundreds of millions of years, specifically in a low-energy, slow-flowing environment, much like a calm river delta. Once on the surface, the rover will survey its surroundings for promising locations and then use its drill to extract soil samples from deep underground. These samples will be delivered to its onboard laboratory for chemical analysis in the hopes of discovering the ancient signatures of life. Beginning this year, the next wave of missions starts its journey to the Red Planet. NASA's InSight mission, the first interplanetary probe to be launched from Vandenberg Air Force Base in California, is preparing for its departure. With the vehicle having already passed its pre-flight checks and been transported to the launch site, it is vital that every component of the lander is in perfect working order. The probe is destined for the equatorial region of Mars, where it will peer deep into the planet's heart. The InSight mission is dedicated to geophysics, aiming to measure the vital signs of Mars. It will listen for the planet's heartbeat, its seismic activity, using a very high-precision seismometer. By employing techniques well established on Earth, scientists will gain a new understanding of the Martian crust, mantle, and core, and the relationship between these layers. The mission will also take the planet's temperature by measuring the thermal gradient of the surface, which reveals how much heat is flowing out from the interior. This is accomplished with a heat flow probe called HP3, which will determine the thermal flux over a full Martian year. Finally, the lander will measure the planet's reflexes by observing how its rotation wobbles in response to the tidal effects of the sun. This last experiment, known as RISE, is designed to provide further clues about the nature of the planet's core. The InSight mission examines the subtle wobble of Mars to help determine the size and composition of the planet's core, yet its scope is broader, serving as an investigation into the interiors of all terrestrial planets. Mars is considered a Goldilocks world. Its size is just right. A larger planet's geology would have erased the ancient evidence scientists seek, while a smaller one may not have undergone the same formative processes as Earth. This makes Mars a unique window into early planetary formation. By studying its interior structure, researchers hope to answer foundational questions about how planets are made, replacing speculation with the hard data this mission is designed to deliver. As robotic exploration continues, the goal of sending humans to Mars gains momentum. NASA, ESA, and Russian agencies are advancing their programs, soon to be joined by missions from China, Japan, India, and the United Arab Emirates. This objective is a pressing priority for NASA and other pioneers. Aerospace corporations are deeply engaged in planning, working to solve immense engineering challenges. A clear consensus has emerged. A powerful rocket is not enough. NASA's SLS and Orion spacecraft are merely two components of a much larger, more intricate system. With renewed focus, NASA is collaborating with partners like ESA, Canada, and Russian space agencies on the Gateway facility. This concept is for a space station in cislunar orbit, the area between Earth and the Moon. It would serve as a multi-purpose hub, a staging post for returning to the lunar surface, a center for collecting moon resources, and a critical assembly point for a flight to Mars and beyond. One commercial partner is Orbital ATK, among 6 companies in NASA's Next Step 2 program, a public-private initiative for deep space exploration. Their plan involves a cislunar staging post built from their successful Cygnus cargo craft. The initial phase would launch a habitat module on an SLS rocket alongside a crewed Orion capsule. In orbit, this outpost would be a platform for experiments and a destination for future crews. By 2025, additional modules would be added to this habitat, enabling deliveries of supplies and experiments while also managing waste. The system's modularity is a key feature, allowing multiple visiting vehicles and creating a base for missions to the lunar surface. Mining for resources, especially water, is considered vital for making long-duration Mars missions more cost-effective. Water can provide hydrogen for fuel, oxygen for breathing, and as an oxidizer, and of course, drinking water. It is understood that permanently shadowed regions on the Moon, particularly at the South Pole, contain water ice, a vital resource for producing hydrogen and oxygen. The Moon's far side also offers a unique advantage, as it is shielded from Earth's radio interference. This makes it an ideal location for a powerful telescope. Building such an observatory with lunar materials, rather than bringing everything from Earth, could open remarkable new avenues for exploring the universe. These crude cislunar missions would also provide invaluable experience for surviving long-duration spaceflight. By 2030, the expanded habitat could become a Mars transit vehicle, supporting demonstration missions lasting 1,000 days or more. The primary contractor for the SLS rocket estimates that a full Mars mission would require 5 or 6 of their launches to get all the necessary hardware into orbit. The need for absolute certainty in all systems before launch is paramount, as there is no quick return from Mars. Once a crew departs, they cannot come back for over 2 years. This is a hard limit imposed by orbital mechanics. The alignment of Earth and Mars in their paths around the Sun creates an efficient launch window only once every 2 years. The journey itself takes 7 to 8 months each way, meaning a crew would have to spend a year at Mars waiting for the planets to align again for the voyage home. A cislunar outpost would foster international and commercial partnerships, enabling lunar exploration and new research. After establishing this presence, the missions to Mars would begin in phases. The first human mission would go into orbit around Mars, not land. This flight would test the deep space systems required for a round trip. Only then would a later mission carry humans to the surface, where they could begin the detailed scientific work of uncovering the planet's secrets. The initial concept for the Gateway, now in development, includes a power and propulsion bus, 2 habitat modules, an airlock, and a logistics module. This core would be resupplied by American and Russian cargo and crew vehicles. Ultimately, the entire assembly could serve as the habitat and transport for long-term exploration of deep space. Lockheed Martin offers a similarly comprehensive vision for a Mars mission. Their plan also uses the cislunar Gateway as a construction platform to build and prepare their Mars base camp for the journey. In this architecture, the Orion spacecraft is an integral part of a larger system that carries all the supplies and scientific equipment needed for the voyage. The Mars base camp is an orbiting station designed with significant redundancy. 4 large solar arrays provide electricity. Propulsion comes from 2 cryogenic stages at opposite ends, fed by 2 large tank farms. Within this structure are 2 habitats and a central living area. The Orion capsule is the crucial command deck, housing all navigation, communication, and avionics. Its inclusion makes the entire craft more reliable and provides the astronauts a proven, safe vehicle for their return to Earth. From this orbiting base, the crew could also investigate the 2 moons of Mars, Phobos and Deimos. They would be able to deploy robotic landers or other automated probes to collect samples from the surfaces of these small, intriguing worlds. Future human expeditions may first involve astronauts exploring the surfaces of Mars's moons. A primary objective for an initial voyage, however, involves the careful confirmation of a suitable landing zone for a subsequent mission that will carry the first human explorers. From their orbital vantage point, these astronaut scientists would have oversight of the entire planet, allowing them to make real-time operational decisions for rovers and drones on the ground. This direct control would guide where to explore, what to investigate, and which surface samples to retrieve for detailed study. One concept for such a mission comes from Lockheed Martin, whose MV lander presents an almost retro-inspired design for a reusable spacecraft. This vision for a launch and landing vehicle is not as futuristic as it might appear, as it is grounded in current technologies, including systems developed for Orion and the Space Shuttle. The principles of reusability and innovation are seen as essential for conquering Mars, as keeping costs manageable is what will ultimately make sustained exploration viable. This drive for feasibility through new thinking is a core tenet of companies like SpaceX. Their direct Mars transport system, the BFR, is designed for a streamlined mission profile. It begins with a liftoff powered by a reusable booster, followed by a brief period in low Earth orbit for refueling. From there, the craft would embark on a direct 3-month cruise to Mars, culminating in a landing straight onto the planet's surface. The spacecraft would then be prepared for its return journey by refueling with resources manufactured locally, before eventually landing back on Earth as a single, fully reusable vehicle. In the meantime, SpaceX has been putting its Falcon Heavy rocket system through testing and readiness for its inaugural flight. One of the most significant challenges for any Mars mission, which the BFR concept addresses in part, is the duration of the cruise. While SpaceX theorizes a 3-month transit, Other NASA-led systems anticipate a journey of 7 to 8 months. Such a long period presents considerable logistical hurdles in housing, feeding, and powering a crew with limited tasks to perform en route. Arriving at Mars much faster would therefore be a profound game changer. An intriguing possibility for achieving this is nuclear power. A technology known as nuclear thermal propulsion, or NTP, could facilitate much quicker transit times, not only to Mars but to destinations beyond. Powered by nuclear fission, the operational concept is remarkably straightforward. Energy released from fission is used to heat a hydrogen propellant to approximately 2,420 degrees Celsius. This superheated hydrogen is then channeled and accelerated through an exhaust nozzle, generating a propellant efficiency about twice that of the most advanced chemical rocket engines. An important detail is that modern NTP systems could potentially be fueled with low-enriched uranium rather than highly enriched material. The physical dimensions of an NTP engine are mostly dictated by the rate at which fission energy can be transferred into the hydrogen propellant, but the actual volume of uranium consumed is quite small, roughly equivalent to a toy marble. By getting travelers to Mars more quickly, NTP could shave months off the trip compared to conventional chemical systems. This reduction in travel time would lessen the mission's payload requirements for food and power, while also minimizing the crew's exposure to the significant risks of deep space, such as galactic cosmic radiation and the effects of microgravity. Furthermore, the maturation of nuclear thermal propulsion technology is expected to foster the successful development of kilopower fission power systems. These compact reactors could be used on the Moon, Mars, and other celestial bodies as a primary in-situ power source for life support, communications, and a wide array of industrial applications. Harnessing these first-generation NTP systems represents a critical first step toward more advanced nuclear propulsion, capable of enabling travel throughout the solar system. The remarkable Cassini spacecraft, along with its companion lander Huygens, has now brought its scientific studies to a close, returning years of invaluable data for scientists to analyze as they plot the next journeys to the Saturnian system. For now, the focus shifts to other planets and other missions, such as Juno piercing the cloudy veil of Jupiter and its distant counterpart, New Horizons, exploring the very edge of our solar system. After a journey spanning 20 years, the Cassini project concluded in a truly dramatic fashion. Yet, as one door closes, another one opens. The enviable task now begins for scientists to unravel the vast dataset that Saturn has just revealed, and by all accounts, they have only just begun to scratch the surface. One reflection on the mission's legacy is that Cassini established a human presence at another world for 13 years, witnessing things we had never imagined and sharing those vistas with the entire globe, thereby inspiring the next generation of missions. A significant issue that scientists confront when exploring this new frontier is the responsibility to leave it in a better condition than they found it. Consequently, eliminating potential problems like space junk or the accidental introduction of terrestrial microbes is a paramount factor in their decision-making. This ethical consideration also helps satisfy planetary protection requirements. In Cassini's case, the goal was to protect the small moon Enceladus, as well as Titan. Both of these worlds are known to harbor global oceans beneath their icy crusts. On the chance that life might exist in those hidden oceans, it was imperative that the unfueled Cassini spacecraft not be allowed to crash into either moon. While the primary focus of the Cassini mission was to investigate the mysteries of Saturn and its rings, the planet's moons proved to be exceptionally worthy of scientific attention. Saturn possesses numerous moons, 62, with confirmed orbits, several of which are only 50 kilometers in diameter. The largest of them is Titan, a world bigger than the planet Mercury. The Huygens module, which traveled aboard Cassini, also made history by becoming the first probe to land on a moon other than our own and successfully transmit data back to Earth. The surface temperature on Titan is a frigid -180 degrees Celsius, yet its landscapes bear a striking resemblance to those on Earth. It has rivers, lakes, and seas, all filled with liquid methane. It even has weather, with rain composed of methane or a mixture of ethane and methane. These meteorological and geophysical phenomena on Titan are reminiscent of processes on our own planet, but the chemical ingredients are fundamentally different. It was Saturn's sixth largest moon, however, that truly excited many scientists. This world, Enceladus, is virtually covered by clean ice and was observed ejecting enormous plumes of water into space. One scientist, whose team discovered the water vapor plume, explained that Enceladus is a compelling destination in the search for extraterrestrial life. Of the four things generally considered necessary for life to arise: a heat source, liquid water, organic material, and stability over time, Enceladus appears to have three. We know there is liquid water under its surface, along with organic material and a source of heat. The only unknown is whether these conditions have remained stable long enough for life to potentially form. Based on the initial Cassini observations made back in 2005, numerous subsequent flybys of Enceladus were conducted. These closer passes have allowed us to understand the Moon much better, including the nature of the organic material present. During one very close flyby, an instrument called the Ion and Neutral Mass Spectrometer gathered critical data on its composition. The exploration of Enceladus revealed its secrets incrementally, beginning with the detection of plumes containing ammonia. Subsequent gravity measurements and detailed imaging unveiled the presence of a global ocean beneath the ice. A pivotal clue came from the Cosmic Dust Analyzer, which found evidence of silicon dioxide nanoparticles, suggesting a process where hot water circulates through rock deep within the Moon. The discovery of molecular hydrogen then provided a final, compelling piece of this narrative. This hydrogen confirmed the existence of these same hydrothermal processes and, more importantly, represented a source of chemical energy, potentially capable of supporting microbial ecosystems within the vast interior ocean. The remarkable longevity of the Cassini mission was what allowed scientists to assemble this intricate understanding of a world like Enceladus. Even in the mission's later stages, the team continued to analyze its data, seeking a deeper comprehension of this remarkable ocean moon. Gathering data is one challenge, but interpreting it to inform future missions is another entirely. This is an area where the Cassini project left a profound mark. It was not only a collaboration among three space agencies, but also served as a fertile training ground for a new generation of scientists who are now developing the skills needed for future projects. The scientific legacy is immense, with project leaders highlighting the cultivation of hundreds of PhDs who will educate future generations, alongside the publication of over 3,000 peer-reviewed papers. The engineering legacy is equally significant, demonstrating how to maximize the capabilities of a complex system, a foundation that future missions will build upon. Furthermore, the international cooperation was a cornerstone of its success, involving 19 nations that contributed hardware and more than 26 nations that have contributed to the scientific analysis. Attention now turns to the mighty planet Jupiter, where the Juno mission is currently conducting its detailed investigation. The story of our solar system is deeply connected to Jupiter, which is believed to be the first planet that formed. Consequently, understanding its origins could help unravel the history of the entire solar system, including how Earth itself came to be. To find these answers, Juno must operate within an exceptionally severe environment surrounding the gas giant. Mission planners dedicated a great deal of time throughout the development process to designing a spacecraft robust enough to function in Jupiter's high radiation fields, its powerful magnetic environment, and the conditions that cause spacecraft charging. By all accounts, the spacecraft's performance in these challenging circumstances has been exemplary. Among the greatest problems for Juno's mission are Jupiter's radiation belts. They are contained within the planet's enormous magnetic field, whose magnetosphere traps and accelerates particles to create intense belts of radiation thousands of times stronger than Earth's own Van Allen belts. During its first pass by Jupiter with all science instruments activated, Juno performed flawlessly. The instruments operated exactly as planned, and the data returned was described as extraordinary. The mission is peering deep into Jupiter, learning about the secrets it holds, but it is also encountering many surprises related to the planet's aurora and the fundamental workings of its atmosphere. The discoveries have been consistently incredible. Subsequent flybys revealed that the immense energy swirling above Jupiter's polar regions was responsible for generating the planet's powerful auroras, but through mechanisms that researchers had not anticipated. What was particularly puzzling to the science team was that these powerful electrical potentials at Jupiter are observed only intermittently and do not seem to be the primary source of the most intense auroras, which is the case on Earth. Juno's camera, JunoCam, was active during these passes, capturing the first ever detailed images of Jupiter's north and south poles. The views were astonishing, revealing a scene quite different from what was expected and bearing little resemblance to the poles of Saturn. Jupiter's poles are covered with a multitude of cyclone and anticyclone storms, some of them larger than half the size of Earth. Researchers are perplexed as to how these storms could form and remain stable in such a configuration. Moreover, the North Pole does not look like the South Pole, leading scientists to question whether this is a dynamic, evolving system or a stable arrangement. They are now investigating if they are witnessing a single stage of a process that will change over the coming year, or if these storms are locked in a long-term pattern, circulating around one another. To find answers about this unique polar activity, engineers are looking deep below the planet's visible cloud tops. The new scientific results from Juno are providing our first close-up view of how Jupiter functions. For the first time, we are able to look into the planet's interior, and what is emerging is that it does not operate at all, as had been predicted. Nearly every existing model for its interior motion, its magnetic and gravity fields, and the workings of its deep atmosphere has been shown to be different from reality. As is common in major scientific endeavors, the findings are resulting in more questions than answers. Juno's original objective was to understand how Jupiter formed, which would in turn help explain how planets in general are made and how our solar system came into being. What researchers are now realizing is that their fundamental understanding of giant planet dynamics was incomplete. The structure of the atmosphere and the interior is far more complex than imagined. While the information gathered so far is undeniably exciting, it represents just a few pieces of a much larger puzzle. The complete picture has yet to emerge. One of those puzzles is the Great Red Spot. While its existence on a turbulent, gaseous planet is not unusual, its scale is immense, covering an area twice the size of Earth. Juno is set to fly directly over this feature, which will be the first time humanity gets a close look at it and what lies beneath its surface. A central question is how deep its roots extend into the atmosphere. Many scientists believe that for a storm to last 300 years, its roots must be very deep. When the spacecraft passes over with its microwave radiometer, it will see if the storm is similar to the surrounding zones and belts, or if it is profoundly different, a question to which no one yet knows the answer. It is not only Jupiter's poles that hold the greatest interest for investigators. They are also intrigued by weather patterns that are unique to this planet, yet familiar in other ways. Studying its atmospheric dynamics helps us understand the atmospheres of other planets, as a great deal of the structure we see on Jupiter, including its storms, looks very similar to what we observe on Earth. On Jupiter, we observe weather systems like cyclones and anticyclones that bear a strong resemblance to storms on Earth. This similarity stems from the principles of fluid mechanics, which are thought to operate consistently throughout the universe. Yet, the two worlds are profoundly different. Jupiter is vastly larger, spins much more rapidly, is composed of different materials, and orbits significantly farther from the Sunday. Here on our own planet, a notable atmospheric pattern is the quasi-biennial oscillation, or QBO. This phenomenon occurs in the stratosphere above the equator, where winds reverse direction from eastward to westward roughly every 2 years. This cycle has a corresponding temperature signature, with the eastward phase being warmer and the westward phase cooler. The QBO is known to influence global climate, acting as a barrier to the transport of aerosols across the equator, and has even been connected to the formation and frequency of hurricanes in both the Atlantic and Pacific Oceans. Understanding these long-term climate cycles on Earth and how they might manifest on other worlds is a key reason for studying both planets. In Jupiter's stratosphere, scientists have identified a comparable pattern called the quasi-quadrennial oscillation. This is a temperature signal observed at the equator, where conditions cycle from warmer to cooler approximately every 4 Earth years. To understand this, a general circulation model was used to simulate the QQO, focusing on the influence of small-scale waves generated by convection deep within Jupiter's clouds. These waves travel upward and are thought to provide the force that compels the stratospheric winds to change direction on their 4-year schedule. The model successfully reproduced not only the timing of the QQO but also the observed temperatures, giving researchers great confidence that they have identified the primary mechanism driving the oscillation. The outer planets offer a natural laboratory for exploring atmospheric physics under conditions far more extreme than those found on Earth. By studying how their climates and atmospheres evolve, we gain deeper insights into the workings of any planetary atmosphere. The Juno spacecraft has been instrumental in this, using a suite of tools to reveal aspects of the gas giant previously hidden from view. One of these instruments is an infrared device called GIRAM, which was designed and delivered by the Italian Space Agency. GIRAM creates thermal maps, essentially showing the distribution of heat across Jupiter. An intriguing detail from these maps is that the centers of many hurricane-like storms are cooler than the surrounding regions. The instrument has also detected very small, isolated warm spots, a finding that is remarkably similar to an observation made by the Galileo probe when it descended into the atmosphere in 1995. What makes the Juno mission truly unique is its pioneering polar orbit. For the first time, a spacecraft is flying a path from pole to pole, passing over the north through its closest approach and then under the south. All previous missions, along with every observation from Earth, were confined to an equatorial viewpoint, which provides a very limited perspective of the polar regions. This new trajectory offers the first clear, unobstructed views of Jupiter's powerful aurora and other polar phenomena. At the same time, as Juno flies directly over the aurora, it passes through the planet's magnetosphere. This allows it to sample, in situ, the charged particles that are spiraling down the magnetic field lines, the very particles responsible for exciting the spectacular light emissions we see. Much like its predecessor Cassini at Saturn, Juno has a finite lifespan dictated by its supply of maneuvering fuel. The prime mission was projected to conclude around its 12th orbit, but NASA retains the option to extend the mission if fuel reserves permit. In that scenario, the spacecraft would be deorbited during its 34th orbit. This final maneuver is a critical part of NASA's planetary protection policy, ensuring the craft does not contaminate any of Jupiter's potentially habitable moons. Juno's pathfinding work is also paving the way for the next generation of explorers, specifically the Europa Clipper. This upcoming mission is currently in its design phase and will focus on a close investigation of Europa, the intriguing moon believed to harbor a vast hidden ocean and thus the potential for life to have evolved beyond Earth. A striking image captured by NASA's departing New Horizons spacecraft from 200,000 kilometers away revealed the delicate blue haze of Pluto's atmosphere, thought to be a kind of hydrocarbon smog. Only a few years ago, the dwarf planet and its 5 known moons were little more than indistinct points of light in the far reaches of our solar system. To truly appreciate the scale of Pluto's place in the cosmos, a simple demonstration can be helpful. If the Sun were represented by a 30-centimeter circle on a beach, one would need to walk about 35 steps to place the Earth, a distance equivalent to 150 million kilometers, or 1 astronomical unit. At this scale, Earth itself would be a mere 3 millimeters in diameter. Pluto's orbit is quite elliptical, ranging from 30 to 50 astronomical units from the Sunday. To place it in this model, one would have to travel a full kilometer down the beach, where the dwarf planet would be represented by a speck just 0.3 millimeters across, a scale that powerfully conveys the immense emptiness of space. An intricate system reveals itself around Pluto, a world far more complex than a simple, frozen object. Its largest moon, Charon, measures about half the dwarf planet's own diameter, and they are accompanied by a family of 4 smaller moons, Styx, Nix, Kerberos, and Hydra. This dynamic orbital dance indicates a surprisingly busy environment. After its flyby, the New Horizons spacecraft spent a full 16 months patiently beaming its precious data back across the solar system, and the resulting discoveries have captivated observers far and wide. When we look closer at the surface, an astonishingly varied and beautiful terrain comes into view. One prominent feature is a vast, bright region of flat plains, the formation of which remains a topic of scientific debate, with a couple of leading theories. Elsewhere, enormous mountain ranges stretch across the landscape, and the surfaces themselves show a wide spectrum of ages. Geologists can see that some areas are heavily marked with craters, signaling great antiquity, while other regions have very few impacts, indicating they are much younger. A particularly remarkable detail can be found in the mountainous regions. The peaks, which rise several kilometers into the thin atmosphere, are actually made of water ice. On Pluto, where the ambient temperature is a staggering negative 230 degrees Celsius, water ice possesses the strength and rigidity of terrestrial rock. It is nitrogen ice that behaves as a softer, more pliable material, forming glaciers. One such feature, a sprawling expanse of nitrogen ice known as Sputnik Planum, is thought to be under 1 million years old, which is exceptionally young by planetary standards. The processes that formed this immense glacier and how it might be renewed are still an open question. Perhaps one of the most compelling discoveries relates to the distinct colors visible across Pluto's surface. These rich hues are now understood to be linked to the presence of compounds called tholins. These molecules are a combination of elements relevant to prebiotic chemistry, the very processes that can precede life. The fact that they have been able to form on planetary surfaces in the extreme cold, so far out in the solar system, has profound implications. It raises the intriguing possibility that for star systems beyond our own, perhaps those with dim stars and distant worlds, the essential molecules for supplying biotic material could be forming right now, far from where anyone expected. Pluto has proven to be a world unlike any previously explored. The 6 gigabytes of images and scientific measurements from New Horizons will give researchers mysteries to unravel for years to come. In the meantime, the probe itself, asleep for the moment, travels ever deeper into the unknown, silently awaiting its next encounter.